begin in the dark the way all good universes do, eyes closed, breath slow, a quiet awareness that something is holding everything together while you rest. If you could peel back the skin of reality, you would not find gears or ropes, or angelic hands. You would find 4 invisible tendencies that never sleep: gravity, electromagnetism, and the 2 nuclear forces we call strong and weak. They do not argue, they do not vote, they simply act always and everywhere, and because of that persistence, your atoms keep their shape, your star keeps burning, and time keeps enough order to mean anything at all. So, before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds, moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. Imagine that nature came with 4 softly glowing dials on a panel the size of your palm. 1 knob for gravity, 1 for electromagnetism, 1 for the strong force that binds the hearts of atoms, and 1 for the weak force that changes one kind of particle into another. This is not a toy box fantasy. Physicists use versions of this thought experiment to test how fragile our world really is. Tonight you get to turn the panel in your hands and listen to what the universe says back when each dial moves. You reach first for gravity, the whispering sculptor of distance and duration. The dial is already set to where you live, so faint it loses arm wrestling matches to fridge magnets, so patient it needs eons to win. Nudge it lower towards 0 and everything that wants to gather dust gas stops gathering. Clouds of hydrogen never collapse, cores never heat, fusion never lights. Galaxies do not condense out of the early mist. There is no Milky Way to swing its spiral arms like lanterns in the night. Space remains a chilly fog with no bright punctuation, a sentence without verbs. Nudge gravity higher and the universe hurriedly overcommits. Matter rushes together too quickly. Stars are born gluttonous and die young. Black holes become not rare endings but the ordinary fate of everything. Between too weak and too strong lies the narrow ledge you stand on now, where orbits close, tides keep time, and a star like the sun burns slow enough for stories to grow brains to remember them. You set gravity back and touch the dial that glows like a filament: electromagnetism. It is the reason there is such a thing as touch. Electrons are pinned to atomic nuclei by this force. Light itself is its travelling ripple. Turn the dial the wrong way to 0 and every atom unthreads in an instant. Electrons wander off, chemistry disbands, colour vanishes, and the great conversation of light between stars and eyes falls silent. Turn the dial too high and bonds clamp so tightly that atoms shrink, spectra shift, and the fragile recipes of water and proteins no longer mix, fold, or taste right. In the quiet of your room, where a phone glows and a heartbeat is an electrical wave, you're living inside electromagnetism's middle register, the one tuned just enough for molecules to be interesting, but not so much that they are impossible. Your fingers hover over the heavy knob, the strong nuclear force, the clenched fist at the center of every atom. It binds protons and neutrons together with an insistence that defies metaphor. Tug at the constituents, and the binding grows stronger rather than weaker, like a rubber band that refuses to snap, and instead births new rubber. In this universe, strong is strong enough to let elements exist beyond lonely hydrogen-carbon frameworks. Oxygen breaths, iron blood. Slide the dial down and nuclei fall apart. Everything heavier than hydrogen evaporates into a primordial monotony. Slide it up, and the nucleus locks too tightly. Stellar alchemy stalls. The delicate pathways that turn helium into carbon and carbon into oxygen go missing. The periodic table, a library of possibilities, shrinks to a pamphlet. The breath you just took depends on that knob resting where it is. Last is the softest sounding dial with the sternest consequences, the weak interaction. Weak does not mean unimportant. It means intimate. It is the quiet permission slip that lets one particle become another, the rare approval that begins the sun's fusion chain. Turn the weak force to 0, and the core of a star chokes on protons that will never convert into the neutrons required to move the reaction forward. The oven cools, dawn fails. Turn it up too high, and stars spend their fuel in a fever lifetimes measured not in billions of years, but in impatient blinks. On Earth, the same shy interaction manages radioactivity and writes part of the planet's internal warmth. In supernovae, it decides which elements will be scattered back to the dark to seed future worlds. The metronome of starlight, the tempo of long afternoons and growing seasons ticks because this dial sits at a value that says not too fast, not too slow. You ease your palm away and the panel remains a small myth. To hold a large truth, the world is precarious and precise. Each dial is a story about range and restraint. None of them announces itself when you pour water or look at the moon, but their combined compromise is the difference between a universe that composes and one that forgets to start. Fine-tuned, some say, and the phrase can sound like superstition. But what it really means in the mouth of a patient scientist is that numbers matter. The strength of a coupling, the mass of a particle, the way a field settles as the universe cools, these are not poetic moods, but measured quantities. If you change them by amounts, you could write on a sticky note 1% here, a sliver there. The architecture of everything familiar would dissolve. There would be no chairs that resist you, no oceans that hold heat, no stable stars pacing the eons with enough patience to cook complexity and let it wake up. It is tempting to call this balance an accident and close the book. It is just as tempting to call it destiny and close the book a different way. Better for tonight to leave the book open and read what the pages actually say. They tell of 4 forces whose strengths are not guessed but tested, whose laws do not merely fit Earth, but reach unchanged into the oldest light we can see. They tell of a coherence that allows you to trace the colour in a sunset to the structure of the atom, and from there to the rhythm inside a star, and from there to the curve of space holding that star in a galaxy's arm. They tell you that harmony can be quiet and still be absolute. There is a final kindness in the panel of dials. It reminds you that fragility and stability can be the same thing seen from different distances. From one angle, you live on a knife's edge, one twist away from silence. From another, you live under 4 guardians that have not flinched in 13.8 billion years, steady as breathing, steady as the tide. The floor under your feet, the pulse in your wrist, the faint streetlight through the window, all of it is rented from their truce. So you lie back and let your mind step into a wider room. The night outside is not empty. It is threaded by gravity's slow hand, lit by electromagnetism's messengers, stitched by the strong force into matter, timed by the weak into futures that last. We will touch each dial in turn and listen more closely. First gravity, because it feels the most familiar even when it is the most strange. But before we begin, keep the panel in your mind a little longer. Feel how light it is, how little effort it would take to spin a knob the wrong way, how quickly the music would stop. And then feel with the same attention how astonishing it is that it doesn't. That while you sleep, the quartet keeps playing and the universe keeps time. If you could watch the universe with your eyes closed, you would still feel gravity. It is not a sound or a touch, but a persuasion, the slow conversation between everything that has mass and everything that waits to be gathered. It's the quietest of the 4 forces, so weak that a small magnet on your fridge can overpower the pull of an entire planet, yet over distance and time, it becomes the shaper of all things. Gravity is patient. That is its power. It does not need strength, only persistence. Imagine a vast cloud of gas adrift in space, a fog of hydrogen cold, and nearly still stretching for light years. In that silence, gravity whispers a suggestion, come closer. Each atom, feeling the collective murmur of its neighbours, drifts inward. At first, nothing seems to happen. The motion is too slow to notice. But century by century, the cloud thickens. Tiny eddies form where density grows, and the whisper turns to pressure. The atoms fall toward their own weight, converting potential energy into heat. Deep in the cloud's heart, a point brightens faint, then fierce, as the temperature crosses 15 million degrees Kelvin. Protons begin to fuse into helium. In that instant, gravity's work gives birth to its opposite light. A star has begun to shine. NASA scientists once called gravity the slow hand of the universe, and it fits. That hand shapes everything we can see. The curve of a planet, the dance of moons, the spiral of galaxies. The Orion Nebula, where newborn stars still burn their first fuel, is a frozen moment in that sculpting. The light spilling from those newborn suns began when invisible attraction became structure. Every sunrise on Earth is an echo of that process, billions of years and trillions of kilometers removed. Now turn the gravity dial to 0 in your mind. The fog of gas refuses to fall. It just drifts forever, dilute. No heat, no compression, no ignition. The cosmos becomes a thin eternal dusk matter scattered, never clumping into stars or planets or you. There would be no orbits, no tides, no time as we know it, because time itself measures change, and gravity is the author of change. In that weightless universe, hydrogen atoms might glide endlessly through infinity, never touching, never making light. A creation without gravity is a creation without story. Turn the dial too high, and the opposite tragedy unfolds. Gravity's hunger becomes insatiable. Every cloud collapses too fast, each newborn star burning its fuel in a brief fury before collapsing into darkness. Galaxies merge into monsters. Black holes devour everything, and the sky fills with nothing but invisible gravity wells, mass so concentrated that even light cannot escape their curves. The universe ends not in stillness, but in choking density matter crushed into silence. Between these two fates, diffusion and collapse, lies the delicate balance that makes everything possible. The Earth you stand on is not static. It is the product of billions of years of falling and stopping just enough. Mountains rise where plates crash, rivers run where valleys bend, and you stay on the ground because space itself is curved around the planet's mass. Einstein showed that gravity isn't a rope pulling you down, it's the shape of the room you live in. Space tells matter how to move, and matter tells space how to curve. That's why the apple falls, why the moon stays in orbit, and why the sun holds its planets like beads on an invisible string. If you could see this curvature, it would look like fabric dimpling beneath every star, every planet, every atom. It doesn't end at the edge of a solar system. The Milky Way itself sits in a vast bowl of gravitational potential, and clusters of galaxies weave those bowls together into the cosmic web. Between the filaments, enormous voids drift almost empty-shaped, not by presence, but by absence, the hollow molds that gravity carved when it pulled matter elsewhere. What's astonishing is how constant this shaping has been. From the first fraction of a second after the Big Bang, gravity has guided the rhythm of expansion. It fought the outward rush of the newborn universe, slowing it just enough that matter could cool and collect. If it had been weaker, expansion would have outrun attraction, no stars, no galaxies, just a frozen mist flying apart. If it had been stronger, the universe would have collapsed back on itself long before atoms or light had a chance to form. The cosmos we inhabit is balanced between those extremes, expansion fast enough to keep going, gravity strong enough to hold form. Every second you are part of that tension. The chair beneath you is pressed against the floor by the same curvature that draws moons and planets into orbit. Inside you, gravity shapes the flow of blood and the rise of breath. Each inhale is a quiet negotiation with the weight of the air. When astronauts orbit Earth, they are not escaping gravity. They are surrendering to it completely, falling endlessly around the planet's curve. To float is not to be free. It is to be in perfect conversation with the pull that never ends. On cosmic scales, gravity also writes the slow poetry of death and rebirth. Stars collapse into white dwarfs, neutron stars, black holes. Galaxies collide, merge and bloom anew. The energy released in those encounters seeds the next generation of worlds. Even now, in the Andromeda Galaxy, 2 million light-years away, gravity is preparing a slow embrace with our own Milky Way. A dance that will take 4 billion years, but is already decided. The night sky you see is a sculpture in motion. And yet, for all its dominion, gravity remains the least understood. We can measure its strength chart, its curves, predict its waves, but we still don't know why it exists at all, why mass bends space instead of merely floating in it. Some physicists search for a quantum particle, the graviton, that might explain it. Others suspect gravity is not fundamental but emergent, a byproduct of information woven through space-time itself. Whatever its true nature, its behavior is universal. The same constant that holds you to the ground binds galaxies across billions of light-years. In that sameness lies a quiet kind of grace. So when you feel the pull of the Earth under your feet, remember it is the faint echo of a cosmic conversation. The same whisper that gathered the first stars still holds you now, patient and exact. You live in the middle of its compromise between the weightless silence of nothing and the crushing silence of too much. Gravity has no language, yet it has written every shape, every orbit, every heartbeat. It is the hand that sculpts the universe and the reason it does not drift apart. Imagine holding your hand out in front of you. You can see it, feel it, trust that it is solid. Yet the truth is, stranger, nothing in that hand is actually touching itself. Every atom in your skin is mostly empty space, a tiny nucleus surrounded by electrons that never collide, only hover in probability. What keeps it all from collapsing or passing through the air? What stops you from falling through the chair beneath you? The answer is the invisible glue of the universe: electromagnetism. It is everywhere and everything. It binds atoms, drives chemistry, carries light, and governs almost every sensation you have ever known. Gravity may sculpt the cosmos, but electromagnetism paints it every color, every spark, every flicker of existence emerges from its rhythm. When you see, touch, hear, or breathe, you are reading the language of this force. At the smallest scale, electromagnetism works through charge. Opposites attract likes repel, a simple rule that builds worlds. The positive protons in the nucleus pull on the negative electrons around them, and that attraction creates the architecture of atoms. But quantum mechanics adds an elegant twist. Electrons cannot simply fall into the nucleus. Instead, they are trapped in a balance between pull and motion, forming standing waves around the core. They occupy orbitals, clouds of possibility, each defined by energy, shape, and spin. That restless dance, the negotiation between attraction and uncertainty, is what gives every element its personality. Hydrogen, carbon, iron, gold, all are variations on the same electromagnetic theme. If electromagnetism vanished for even a fraction of a second, every electron would drift away from its nucleus, every atom disintegrate, every solid melt into radiation. You would not fall apart, you would cease to exist, replaced by a uniform sea of unbound particles. In that moment, all color, all heat, all life would vanish, because light itself is another face of the same force. Light is electromagnetism set free, a ripple of its field traveling through space. In 1865, James Clerk Maxwell wrote down 4 equations that tied electricity and magnetism together, and found to his astonishment that they described waves moving at the speed of light. From that day forward, light was no longer mysterious. It was electricity and magnetism chasing each other through the vacuum, a self-sustaining duet of electric and magnetic fields, one creating the other as they moved. Every flash of lightning, every aurora, every ray of sunlight is a living example of those equations. A photon, the particle of light, carries no mass, no charge, yet it is the perfect messenger. Because it is massless, it can never slow down. It always travels at the same cosmic speed limit, 29792 meters per second. That constancy gives electromagnetism infinite reach. A photon born in a star 10 billion light-years away can cross the expanding universe, slip between galaxies, and arrive in your eye with its identity intact. It has crossed epochs without aging, carrying a story older than Earth itself. Photons are not only light, they are also the mediators of electromagnetic force. When 2 electrons repel each other, they do so by exchanging virtual photons, tiny messengers, flickering in and out of existence faster than any measurement can catch. These unseen trades are the reason your chair doesn't collapse beneath you and your body doesn't merge with the air. Every time 2 atoms resist overlapping, they are holding a silent conference in photons, agreeing to keep their distance. This dance is precise beyond imagination. The strength of the electromagnetic interaction is set by a number known as the fine structure constant, often written as approximately 1/137. Physicists have measured it to extraordinary precision, and it governs everything from the color of light emitted by hydrogen to the stability of chemical bonds. If A were even slightly different, say 36 or 138, the consequences would be catastrophic. A stronger force would pull electrons too close to nuclei, shrinking atoms and making chemistry impossible. A weaker one would let electrons drift too far, leaving molecules fragile and unstable. Stars would burn at the wrong pace, and the photosynthesis that feeds every living thing would fail. The fact that it sits exactly where it does is one of nature's quiet miracles. On cosmic scales, electromagnetism sculpts more than atoms. It drives the brilliant violence of solar flares, arcs of plasma taller than planets hurled from the sun by tangled magnetic fields. It powers the aurora borealis when charged particles spiral down Earth's magnetic field and strike atoms in the upper atmosphere, painting the sky in ribbons of green and violet light. It shapes galaxies where magnetic filaments guide streams of dust and gas into glowing arms. The force that binds your hand to matter also threads through the Milky Way's heart. The paradox is that despite its ubiquity, electromagnetism almost cancels itself out on large scales. Most of the universe is electrically neutral. For every proton there is an electron, and their opposite charges balance perfectly. That is why gravity so weak, so patient dominates over cosmic distances. But within matter inside the tiniest spaces where neutrality breaks, electromagnetism reigns supreme. It determines the shape of snowflakes, the conductivity of copper, the warmth of fire, the rhythm of your heartbeat. Your brain itself is a storm of electrical impulses guided by this same field, thoughts leaping from neuron to neuron through electromagnetic waves. Even technology is its echo. Every Wi-Fi signal, every radio broadcast, every photograph ever taken, all are electromagnetic waves tamed by design. Maxwell's equations became the blueprint for civilization. Our satellites speak to Earth through radio photons. Our eyes read reflected light. Our solar panels drink in the sun's radiance, converting it back into current. From lightning to microchips, the story has never changed. It's all one field, manifesting in different keys. And yet the deeper we look, the more enigmatic this force becomes. Why does A equal 137? Why does the photon have no mass? The standard model of physics predicts how electromagnetism behaves with flawless accuracy, but it does not explain why the numbers are what they are. Richard Feynman called the fine structure constant one of the greatest damn mysteries of physics. He meant that behind the elegance of Maxwell's equations lies an unanswered question. Why is the universe tuned so that light and matter fit together so perfectly? Perhaps in the earliest moments after the Big Bang, electromagnetism was not alone. It was one facet of a deeper unity later fractured as the cosmos cooled. Perhaps what we call light is just one surviving strand of that ancient whole. Whatever its origin, electromagnetism remains the most expressive of all forces, invisible, infinite, intimate. It holds your atoms, writes your memories in electrical pulses, and lets you see the stars whose photons left their suns before the first humans ever stood beneath the sky. So the next time you notice the glow of a screen, a spark, or a sunset, remember what you're witnessing: an endless conversation between charge and field matter, and motion, distance, and time. You are touching the universe's most fluent language, the invisible glue that holds it all together, humming across infinity at the speed of light. Before you were ever born, before Earth had an ocean to reflect the sky, there was light. Not just illumination, but structure, temperature, rhythm, the visible signature of the invisible. Every shade of blue or flame of gold you've ever seen is one fragment of a single continuous force. Electromagnetism, the quiet translator between matter and energy. If gravity sculpts the stage of existence, electromagnetism paints it in fire and colour. 2 centuries ago, this idea would have sounded like poetry. Electricity and magnetism were curiosities, then sparks from amber rubbed, with fir-iron needles twitching toward north. They seemed separate, almost magical. It was James Clerk Maxwell who first saw through the illusion. In 1865, he gathered the fragments into 4 elegant equations that merged electricity, magnetism, and light into one. Those lines of mathematics revealed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric one, a self-sustaining wave moving through the vacuum at a constant speed. When Maxwell calculated that speed, it matched the measured velocity of light itself. The conclusion stunned him. Light is an electromagnetic disturbance. With that realization, the colors of the world were no longer divine mysteries or artistic metaphors. They were measurable consequences of fields vibrating in harmony. Every rainbow, every radio signal, every heartbeat visible on a hospital monitor stems from that same discovery. Maxwell's unification was the first great triumph of modern physics, the recognition that nature uses her patterns, that what flickers in a wire also shimmers in a star. To understand the scale of that unification, hold a simple image: a photon leaving the surface of the sun. It slips free of charged particles in a boiling sea of plasma and begins its journey across 150 million kilometers of emptiness. Along the way, it dodges planets, passes through magnetic storms, and after 8 minutes touches your skin. That warmth is not an abstract number, it is a handshake across space. The sun's surface is a cauldron where electromagnetism both traps and liberates energy. Magnetic fields tangle, twist and snap, hurling flares 1 million kilometers high. Solar observatories such as NASA's Parker Solar Probe have recorded those arc loops of charged plasma glowing brighter than anything on Earth. The sun is a magnetic creature. alive with invisible lines that writhe like serpents in slow motion, their movements sculpting both radiation and rhythm for every world that orbits nearby. The same cosmic art plays closer to home. At Earth's poles, charged particles from the sun spiral down magnetic field lines and collide with the thin air of our upper atmosphere. Oxygen atoms glow green, nitrogen, violet, and the night blossoms with curtains of colour. The aurora is not merely light, it's a story written in our electromagnetic ink telling of a planet that protects itself with an invisible shield. Each shimmer is an atom returning from excitement to calm, releasing a photon as a sigh of relief. The aurora, the sunrise, the flicker of a candle, all are local dialects of the same universal language. Every interaction of this force obeys a single number, the fine structure constant at approximately 1137. It appears everywhere light and matter meet. Physicists call it dimensionless, because it has no units, pure proportion, an intrinsic fingerprint of the universe. A determines how strongly charged particles interact and how light behaves when it touches them. It is why the sky scatters blue more than red, why stars burn with specific colours, why molecules hold their shapes, why chemistry is possible at all. If A were even slightly different, the spectrum of the sun would shift, photosynthesis would falter, and life would lose its palette. The green of the aurora, the amber of dawn, even the red of blood owe their existence to a fraction that never changes. Richard Feynman used to tell his students to write 1137 on their desks as a reminder of mystery. You might say he wrote that the hand of God wrote that number. He didn't mean religion, he meant awe. For all our equations, no one knows why A takes that value. It's as if the universe tuned its own instrument and left us to play by ear. Every measurement we make, from hydrogen spectral lines to the spin of electrons in distant galaxies, confirms that A has remained unchanged for 13.8 billion years. The same constant governs the birth of stars and the glow of your screen. Across time and distance, the universe never forgets its key signature. This constancy is what lets electromagnetism become not only a physical law, but an aesthetic one. When light passes through a prism and fans into a rainbow, you are watching A in performance. When a distant nebula shines in infrared or a quasar blazes in ultraviolet, those colours are the notes of its cosmic symphony, determined by the energy steps electrons are allowed to climb and fall. The stronger the field, the higher the note, the weaker, the gentler the hue. The universe hums in octaves of frequency from radio to gamma rays, all born of Maxwell's marriage of electricity and magnetism. Consider too how this same force creates form. In the heart of a thunderstorm, friction strips electrons from droplets, building an imbalance so fierce that the air itself breaks. A lightning bolt is the atmosphere repairing its own asymmetry, an electric current tearing through miles of sky to rewrite equilibrium. The flash lights the clouds, the thunder rolls, and for a moment you witness the raw energy that underlies every heartbeat and every circuit. It is the same power contained, refined and gentled in every battery, every signal, every neuron. Without electromagnetism, there would be no temperature, no visible universe, no memory. Heat itself is simply the random jostling of charged particles, the electromagnetic push and pull of atoms in motion. The warmth of sunlight on your face, the red glow of cooling metal, the orange of a campfire, each is matter, speaking in the language of photons. Even our perception of touch is electromagnetic when you press your fingertips against glass. The atoms in your skin never truly meet those in the glass. The repulsion between their electrons stops them a billionth of a centimetre apart, yet to your nerves, that resistance feels like solidity. You are never really touching anything. Electromagnetism is touching for you. Maxwell could not have imagined what his equations would become the backbone of civilization. They describe the behaviour of light across the cosmos and the flow of current in every power line, every satellite signal, every heartbeat monitored in a hospital. They are written in the same form for a candle flame and a distant quasar. Einstein once said that the happiest thought of his life was realizing how relativity completes Maxwell's symmetry, showing that light's constant speed is not a coincidence but the foundation of space and time themselves. When you step outside tonight and see a star shimmer above the horizon, think of what you're really seeing: a photon that left its birthplace long before humans learned to name the constellations, a messenger of electromagnetic order still vibrating with the same fine structure, constant, that shaped it. In that faint glow is every sunrise that has ever been, and every equation scribbled on a chalkboard to explain it. Fire and colour magnet and field light, and life, all are signatures of one universal rhythm humming quietly through you even now. The sun, the aurora, the pulse in your wrist, they're all Maxwell's masterpiece playing on, repeat across the cosmos. If electromagnetism gives the universe its color and shape, the strong nuclear force gives it substance, the deep binding that keeps matter from disintegrating into dust. It is the fiercest of the four cosmic forces, yet also the most hidden. It does not reach across rooms or light years. It holds its breath inside the smallest spaces imaginable, gripping the heart of every atom. Without it, nothing solid would exist, no carbon, no iron, no starlight, no you. To find it, we have to journey inward far beyond the atom's cloud of electrons past the protons and neutrons inside its nucleus, into a realm where distance is measured in trillionths of a millimeter. Here the ordinary rules of magnetism and gravity dissolve. Protons and neutrons, once thought indivisible, are themselves composite trios of smaller particles called quarks, bound together by the strong force. Quarks carry a peculiar property physicists call color charge, not color, in the visual sense, but a symbolic way to describe how they attract and balance each other. Three quarks of differing colors join to make a proton or neutron perfectly neutral, when combined the way red, green and blue light merge into white. The agents that hold them together are gluons, aptly named. They are the messengers of the strong force darting between quarks at nearly the speed of light, weaving an unbreakable web. But unlike photons, which glide freely through space, gluons themselves carry the color charge. This makes the strong force unique. The field reinforces itself. The farther apart quarks try to drift, the more fiercely the gluons pull them back. Try to pry them apart, and the energy you spend only creates new pairs of quarks instead. In the language of quantum chromodynamics, QCD, we call this property confinement. Quarks are never found alone. Nature forbids isolation. Every attempt to separate them results not in freedom, but in multiplication, matter birthing more matter. The paradox is beautiful. Inside that confinement hides another truth. When quarks move close together, their grip on each other weakens. At distances smaller than a proton's diameter, the strong force slackens, letting quarks behave almost freely, as if they were independent. This counterintuitive behavior is known as asymptotic freedom, discovered in the 1970s by Gross-Politzer and Wilczek, a revelation that earned them the Nobel Prize. It means the strong force is both cage and sanctuary, tight at large distances, loose at small ones, a perfect balance between imprisonment and cooperation. The more you try to separate what belongs together, the harder the universe works to repair the bond. That bond is not merely symbolic, it is energetic. Einstein's famous equation, E mc2, is nowhere more alive than inside the nucleus. The energy of the strong force manifests as mass. The mass of protons and neutrons arises mostly not from the quarks themselves, but from the restless motion and tension of the gluon field between them. In other words, almost all the matter in your body, nearly everything you weigh, is energy frozen by confinement. You are built of fields under pressure-condensed light. This internal furnace powers the stars. When 4 protons fuse into one helium nucleus, a tiny fraction of that binding energy is released as light and heat. That fraction, multiplied by the sun's unimaginable number of reactions per second, becomes the daylight on your skin, the wind in the trees, the entire biosphere's heartbeat. In that moment, the strong force locked deep inside atomic cores becomes visible as sunlight. The cosmos radiates not from creation alone, but from continuous release nuclear glue turning back into brilliance. Every element heavier than helium owes its existence to this same violence. In the cores of massive stars, gravity compresses matter until atomic nuclei are forced so close that the strong force allows them to fuse into new configurations, carbon-oxygen-iron. But once iron forms, the equation changes. It is the most tightly bound nucleus, the point where fusion no longer yields surplus energy. When a star pushes past that limit, it can no longer hold itself against gravity's inward pull. The result is collapse of supernova, and in that collapse the strong force reveals its final generosity. Under extreme compression, protons and electrons merge into neutrons, releasing neutrinos and shattering the star apart. For a brief instant, temperatures exceed billions of degrees, and the shock wave creates the heaviest elements, gold, uranium, the calcium in your bones, all born from a final catastrophic negotiation between gravity's demand and the strong force's refusal to break. Inside those exploding furnaces, energy quite literally becomes matter. Pair creation photons turning into particles is the inverse of fusion's glow. Each time light condenses into mass, the strong force catches it and holds it in place, adding another brick to the cosmic edifice. In the first microseconds after the Big Bang, the universe was nothing but a quark-gluon plasma, a perfect dense soup of free color charges. As the cosmos expanded and cooled, the strong force froze out, trapping quarks into protons and neutrons. Matter as we know it began when confinement set in, when the glue hardened. Even now, physicists are trying to recreate that primordial moment. In the tunnels of CERN's Large Hadron Collider, gold and lead nuclei are smashed together at near-light speed, briefly melting their components into the same quark-gluon plasma that existed 13.8 billion years ago. Detectors record the spray of particles and the flickering jets of energy as the plasma cools and hadrons composite particles, like protons, reform. What they see confirms the dual nature of the strong force chaos that breeds structure confinement, that gives freedom its boundaries. It's almost poetic that the strongest force in the universe has such a short reach, less than the width of an atomic nucleus. Strength does not need distance to matter. It needs purpose. The strong force doesn't hold galaxies, it holds possibility. It ensures that the smallest pieces of reality are not dust but architecture. It is the reason hydrogen can fuse, the reason stars can shine, the reason you can hold a thought in a brain made of atoms that have survived billions of years of collapse and explosion. So when you look at your hand again, that same hand once held together by electromagnetism, remember that beneath its surface, at scales too small to imagine, trillions of quarks are bound in endless conversation, exchanging gluons in a rhythm older than time. Their confinement is your coherence. Their tension is your weight. You are in the deepest sense the offspring of a force that never lets go. The universe endures because somewhere between freedom and binding, between chaos and order, the strong force decided that together was better than apart. If the strong force is the muscle of the atom and electromagnetism its light, then the weak nuclear force is its pulse, faint, patient, yet indispensable. It is the quiet clock that keeps stars burning at the right pace, the hidden switch that allows matter to change its identity, and the author of one of the universe's most elusive stories, The Flight of the Neutrino. You've never felt the weak force, but it passes through you endlessly. Right now, trillions of neutrinos born in the sun's core are streaming through your body every second, barely touching a single atom. They are the quietest messengers in existence, so indifferent to matter that a lead wall a light year thick would hardly slow them down. And yet, without the weak interaction that created them, there would be no sunlight at all, no warmth on your face, no time for life to evolve. The cosmos would shine for a heartbeat and then go dark. To understand, the weak force returned to the heart of a star. Deep in its core, protons crash together under immense pressure, trying to fuse into helium. But two protons cannot stick. Their identical charge makes them repel each other, and the strong force cannot bind them directly. Here, the weak interaction performs a small but crucial miracle. It allows one of those protons to transform into a neutron. In that instant, a particle called a W boson is emitted, a carrier of the weak force. The W boson lives only a trillionth of a second before decaying into a positron, an anti-electron and a neutrino. What remains behind is a proton-neutron pair, the seed of helium. Multiply that by 10 to 28 times per second and you have the sun. This transformation is so rare that it sets the sun's entire tempo. If the weak force acted faster, fusion would race ahead, burning the sun's fuel in thousands of years instead of billions. If it was slower, the chain reaction would stall, and the sun would never ignite. The delicate pace at which stars live and die, and the time it took for life to arise on Earth, are gifts of this subtle, unhurried interaction. It is cosmic patience made physical. The weak force governs more than the hearts of stars. It is also the clock of decay. When unstable nuclei on Earth emit radiation, they are performing the same act of transmutation that powers the sun. A neutron inside an atom may suddenly become a proton, releasing an electron and an antineutrino. We call this beta decay, and it is the quiet reason radioactive elements change over time. The glow of radium, the heat inside the Earth's crust, the carbon-14 that lets us date ancient bones, all are signatures of the weak interaction whispering through matter. Unlike gravity or electromagnetism, which have infinite range, the weak force operates at subatomic distances. Its mediators, the W and Z bosons, are massive, about 90 times heavier than a proton, and their weight limits their reach to less than a tenth of a proton's width. But that heaviness also gives them power. They can turn one kind of particle into another. They are in a sense the universe's translators, allowing protons to become neutrons, electrons to become neutrinos, matter to shift flavors. Without them, chemistry would be static stars, lifeless, and the cosmic story short. The discovery of these bosons was a triumph of human persistence. For decades, physicists suspected their existence from the fingerprints left in radioactive decay. In 1983, CERN's superproton synchrotron finally detected them, tiny fleeting blips that confirmed a grand unification. The electroweak theory, which showed that electromagnetism and the weak force are two expressions of a single underlying field. At high energies, as in the early universe, they were one. Only as the cosmos cooled and the Higgs field took on its current value did the symmetry break, leaving two familiar but separate forces. In that symmetry breaking, the universe gained diversity, light and decay, photons and neutrinos, permanence and change. If you could watch this force work inside you, you would see it shaping even the planet's heat. The weak interaction drives the slow decay of uranium and thorium deep in Earth's mantle, providing warmth that keeps the core molten and the magnetic field alive. It is a geologic heartbeat echoing the stellar one. Without it, tectonic plates might freeze in place, the atmosphere would stagnate, and the cycle of renewal that supports life would falter. And then there are the neutrinos, the ghosts born wherever the weak force stirs. They come from nuclear reactors, exploding stars, and the Big Bang itself. When a massive star collapses in a supernova, the weak force takes center stage. In a fraction of a second, electrons and protons are crushed into neutrons, flooding space, with a burst of neutrinos so vast that they carry away most of the explosion's energy. Those ghostly particles race across galaxies, passing through worlds unnoticed, yet they record the instant a star died. In 1987, detectors on Earth captured 24 neutrinos from a supernova in the Large Magellanic Cloud, the faint heartbeat of a sun, 160,000 light-years away. For a moment, humanity held a message written in the weak force itself. Despite its name, this is not a timid force. It reshapes matter, defines time, and mediates balance between existence and decay. Its weakness is precisely what gives the universe time to breathe. The half-lives it governs, from seconds to billions of years, are the metronome of evolution, geology, and memory. Every isotope that slowly changes, every star that lingers before collapse, every body that stays warm by the radioactive hum of the Earth, owes its rhythm to this invisible clock. Perhaps that is the weak force's truest gift: endurance through subtlety. It does not sculpt like gravity or dazzle like light. It whispers through transformations so small they are almost overlooked, yet those whispers are what keep the cosmos alive and changing. It is the reason stars age gracefully, rather than explode at birth, the reason elements form in steady succession, the reason decay and renewal coexist. So as you lie beneath the same stars it governs, imagine that somewhere in their depths protons are turning to neutrons, neutrinos are slipping through space, and the universe's faint pulse continues. It has been ticking since the dawn of time, a clock that never stops, never hurries, never rests, the quiet heartbeat of creation. In the beginning there was no light, not because the universe was dark, but because there was no distinction between light and the forces that would one day create it. The cosmos was still young, less than a trillionth of a second old, a storm of energy, so dense that particles and fields blurred into one. In that incandescent chaos, symmetry reigned. Gravity, the strong force, and the electroweak force, a union of electromagnetism and the weak nuclear interaction, were facets of a single harmonious whole. Nothing had mass, everything moved at the speed of light. It was a universe without friction, without boundaries, without form. This is where the story of symmetry breaking begins, the moment when perfection gave way to diversity, when the uniform glow of creation fractured into the patterned habitable world we know. As the universe expanded, it cooled like breath condensing on glass. When it dropped below 10 quadrillion degrees Kelvin, the electroweak force could no longer hold its unity. A new field began to ripple through space, a field that would forever change the meaning of mass and light. Physicists call it the Higgs field. Invisible, omnipresent, it filled the cosmos like fog fills a valley, altering the behavior of everything that moved through it. At first, every particle danced freely, massless and swift. But when the Higgs field condensed like dew forming out of air, it created a drag, a resistance that affected some particles more than others. The carriers of the weak force, the W and Z bosons, stumbled as they moved through this new medium and became heavy. The photon, the carrier of light, felt nothing and remained massless. In that instant, the universe split the electro-weak force into two, the weak nuclear force confined to the heart of atoms and electromagnetism, the endless radiant tide that carries light across space. That separation was the first great act of cosmic differentiation, the universe learning to specialize. It was also a necessary loss of symmetry. Perfect symmetry is sterile. It permits no difference, no structure. Breaking it allows the cosmos to invent, to choose some pathways and not others, to create imbalance and with it possibility. Imagine that symmetry as a perfectly round hill with a marble resting at the top. Before the Higgs field formed, the marble sat in balance, all directions equal. But as the universe cooled, the shape of the hill changed into a valley. The marble rolled down and came to rest somewhere on its slope, breaking the perfect symmetry of before. The direction it chose became the definition of reality, which particles would gain mass, which would stay free, and how the laws of physics would thereafter unfold. That tiny tilt in the cosmic landscape determined everything from the light of stars to the structure of DNA. In the decades that followed, humans would try to glimpse this hidden field that changed the fate of the cosmos. The mathematics of the Standard Model predicted its existence, but for nearly half a century, the Higgs boson, the quantum particle associated with that field, remained a ghost too massive to be created in any accelerator we had built. Scientists nicknamed it the God particle, not for any divine reason, but because it seemed essential and unreachable. Then, on a July morning in 2012, the detectors at CERN's Large Hadron Collider registered a resonance at about 125 giga-electronvolts, the unmistakable fingerprint of the Higgs boson. It was a tremor from the moment the universe first learned to distinguish between light and matter, weak and electromagnetic. For the first time, we'd caught the echo of symmetry breaking in our own machines. A particle born 13, 8 billion years ago in the first instance of time, had appeared again under a mountain on the Franco-Swiss border. Its discovery completed the Standard Model, a framework describing all known fundamental particles and forces except gravity. But more than that, it confirmed that mass itself is not an inherent property, it is an interaction. Things have weight because they talk to the Higgs field. The stronger the conversation, the heavier they become. A top quark deeply entangled with the field gains enormous mass. A photon silent glides through, untouched. Your own body, its inertia, its resistance to motion, is the echo of that cosmic dialogue still ongoing in every particle you contain. The consequences of that ancient transition are everywhere. When the weakened electromagnetic forces parted ways, the universe gained texture. Matter slowed down enough to gather to clump under gravity's hand to build stars, galaxies and planets. Light began its long voyage through transparent space. The same break that fractured unity made endurance possible. Without mass, atoms could never form. Without photons, nothing could be seen or felt. Symmetry breaking was not destruction, it was creation by distinction. And yet, deep within that act lies a lingering question. Why did the Higgs field choose the value it did? The number that sets the Higgs energy, about 246 billion electronvolts, appears finely tuned. If it had been even slightly higher, particles would be too heavy, the universe too dense, collapsing back on itself. Slightly lower and mass would be too light chemistry, too fragile stars unable to ignite. The balance between lightness and weight, between radiation and matter, hangs on a razor's edge drawn at the dawn of time. Some theorists dream of restoring that lost unity through a grand unified theory, a framework where all four forces merge again at unimaginable energies. Others suspect that the Higgs field is a doorway, not an endpoint, that its value hides clues about parallel universes, dark energy, or the shape of space-time itself. But for now, what we know is enough to inspire awe. The Higgs field did not vanish after symmetry broke. It still fills the cosmos, constant and silent, giving everything the ability to resist motion, to exist with identity rather than blur into light. You can think of it as a kind of cosmic memory. Every atom you touch carries within it the record of that first transition. Every bit of mass around you is the fossil of broken symmetry. And while the electro-weak split may have been the universe's first loss of perfection, it was also its first act of self-definition the moment physics became personality. The stars that burn the photons that reach your eyes, the weight of your own heartbeat, pressing against the world, all of it began when symmetry yielded to difference. The Higgs field rolled in like mist across a cooling landscape, and from it emerged light matter and the long unfolding story of everything that can change. Before Einstein, gravity was a pull, an invisible hand stretching across the void. Isaac Newton described it as a mysterious attraction between masses, a force that stitched the cosmos together with perfect predictability. His equations worked so well that for 2 centuries no one thought to question why things fell. The apple dropped, the planets orbited, and that was enough. But Einstein saw something different hiding behind the arithmetic, not a force, but a shape. In 1915, he proposed a vision that would upend our understanding of reality, that gravity is not a tug between objects, but the very geometry of space and time bending around mass and energy. The sun doesn't pull the Earth, it warps the stage on which Earth moves. The planet simply follows the straightest possible path through a curved arena, a path that loops into orbit. To picture this, imagine a rubber sheet stretched tight. Drop a heavy ball in the center and the surface dips. Roll a smaller marble across the sheet and it curves around the dip, not because the ball reaches out to grab it, but because the sheet itself is bent. Now erase the sheet and think bigger 3 dimensions of space, plus time itself, all woven into a single fabric called space-time. Every star, planet and particle leaves its own subtle dimple in that fabric, telling the rest how to move. Space tells matter how to fall, matter tells space how to curve. Einstein's idea was radical. Too radical at first. The equations of his general theory of relativity were elegant but untested. Then, in 1919, proof arrived from the heavens. During a total solar eclipse, British astronomer Arthur Eddington photographed stars whose light grazed the edge of the sun. According to Newton, their apparent positions in the sky should remain fixed. According to Einstein, space-time curvature would bend their light slightly inward. When Eddington developed the plates, the starlight had indeed shifted by precisely the amount Einstein's theory predicted. Overnight, a quiet German patent clerk became a prophet of a new cosmos. Headlines read, "Revolution in Science Newtonian Ideas Overthrown." Since then, the evidence has only deepened. We've watched light bend around galaxies in a phenomenon called gravitational lensing, where invisible clusters of mass act like cosmic magnifying glasses. We've tracked time itself slowing near massive objects. Atomic clocks on airplanes tick more slowly than those on the ground. GPS satellites must correct for this curvature daily, or your phone would misplace you by kilometers within minutes. What Einstein imagined as pure geometry has become a daily part of navigation technology, and even our sense of now. But nowhere is curvature more dramatic than at the edge of a black hole, a place where space-time folds in on itself so completely that the concept of distance dissolves. The first image ever captured of one in 2019 by the Event Horizon Telescope showed a glowing ring of gas swirling around a shadow, not the hole itself, but the absence it creates. Light skims the brink, looping around the abyss before escaping. Inside that boundary, gravity curves space so tightly that every path, even for light, turns inward. Time slows, stretches, and finally halts. It is the ultimate punctuation mark of Einstein's equations, a place where geometry collapses into mystery. For decades, black holes were mathematical ghosts doubted even by Einstein himself. Yet the universe turned out to be full of them, stellar remnants, millions of them, and supermassive giants anchoring nearly every galaxy. The one at the Milky Way's core, Sagittarius A, holds 4 million times the mass of our Sun in a region smaller than Mercury's orbit. Its gravity sculpts the orbits of nearby stars into perfect ellipses, proof of relativity's quiet dominion over even the most chaotic regions of space. And still, Einstein's tapestry moves. In 2015, a century after his prediction, the LIGO Observatory detected the faintest vibration ever recorded, a ripple in space-time itself. 2 black holes had collided a billion light-years away, shaking the universe like a distant drum. The signal lasted less than a second, a chirp rising in pitch, as the holes spiraled together and then silence. That whisper confirmed one of relativity's most haunting promises, that when massive bodies accelerate, they send waves of curvature through the cosmos, stretching and compressing the very metric of space. Since then, LIGO and its sister observatories have heard dozens of such murmurs, neutron stars colliding black holes, merging the universe, ringing with invisible sound. Each detection is a letter from space-time itself, written in vibration rather than light. For the first time, we are listening, not just looking at gravity. Einstein's insight reshaped not only physics but our philosophy of existence. Gravity, once the simplest of forces, became the storyteller of time, dictating how clocks run and how history unfolds. The passage of time itself depends on where you stand in the gravitational landscape. A second near a black hole is not the same as a second on Earth. The universe does not share one rhythm, it plays a symphony of tempos all conducted by curvature. And yet there is something tender in this revelation. The same mathematics that describes galaxies also describes the fall of a raindrop. The same geometry that warps starlight also curves the space around your feet. You live inside the very fabric that bends for suns and collapses for black holes. When you look up, the light you see has taken the scenic route through valleys of space-time carved by distant masses. Every shimmer in the sky is an echo of geometry. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." He meant that the human mind, made of atoms bound by these same laws, can still imagine the curve of space-time. Perhaps that too is a kind of symmetry, the thinker and the thought obeying one design. So the next time you drop a stone or watch a planet cross the night, remember nothing is pulling it down. It is simply following the contours of a universe still rippling from ancient collisions, still bending and breathing. Space itself is not empty. It is alive, curved, singing, and endlessly patient. If the strong force builds the nucleus, and electromagnetism binds the world of atoms, then gravity, the weakest of them all, commands everything else. It is the quiet emperor of the cosmos, a ruler so patient and so pervasive that even the stars obey. Measured on paper, gravity is absurdly feeble between two protons. The electromagnetic repulsion is 1036 times stronger than their gravitational attraction. Yet gravity wins in the end. Galaxies, planets, oceans, and human feet on solid ground all exist because of a force so weak that it might as well be a whisper, except that it never stops whispering. Its secret is not strength, but universality. Every particle with mass feels it, every photon with energy bows to it. Unlike electromagnetism, which can cancel itself out through positive and negative charge, gravity has no opposite sign. There is no negative mass to balance the books. Every speck of matter in the universe pulls on every other, the effects adding endlessly instead of neutralizing. The result is cumulative. What starts as an imperceptible tug between two atoms becomes the architecture of entire galaxies. The second secret is infinite range. The strong and weak nuclear forces fade after subatomic distances. Electromagnetism dies out when charges balance. But gravity persists across the full span of the universe, its reach unbroken by emptiness. A single hydrogen atom exerts a gravitational pull that in principle extends beyond the most distant quasar. It never vanishes, only grows thinner, slower, more patient. Over cosmic timescales, patience becomes power. That persistence gives rise to structure. In the early universe, when matter was spread almost perfectly evenly, gravity sought every small imperfection. A slightly denser patch here, a subtle fluctuation there, each became a seed. Over billions of years, those seeds drew in more matter, forming the first stars, galaxies, and clusters. Where electromagnetism could sculpt only atoms, gravity carved filaments of cosmic web stretching across hundreds of millions of light years. If the strong force builds bricks, gravity is the hand that stacks them into cathedrals. Yet this universality hides a paradox. How can something so weak produce order so vast? The answer lies in the balance between pull and expansion, the oldest tension in existence. After the Big Bang, space itself began to stretch not through motion, but through the creation of more space between things. Gravity resisted gathering matter into islands against that outward tide. For most of cosmic history, this duel was evenly matched. Galaxies grew merged and swirled into spirals, all while the universe continued to expand in a steady rhythm. Too much gravity and everything would have collapsed back into a fireball. Too little and matter would have dispersed into a thin mist. The universe we inhabit, intricate, stable, alive, exists because gravity's weakness was precisely enough. That balance is so delicate that even the smallest deviation would have erased the possibility of galaxies. Cosmologists call this the flatness problem. The density of the universe, compared to the critical density needed for balance, differs by less than 1 part in 100 trillion. Somehow, gravity managed to tune the cosmic expansion rate to near perfection, neither runaway nor doomed to recollapse. It is a precision so implausible that physicists invoke early universe inflation To explain it, a brief exponential expansion that set the stage for gravity's patient rule. Out of apparent weakness emerged exactness. There's poetry in that restraint. Gravity's equations, the Einstein field equations, are nonlinear, subtle, and unforgiving. They govern the dance of black holes and the drift of galaxies with the same precision they apply to an apple or a clock. They do not shout, they whisper in the language of curvature. A tiny miscalculation in one corner of space-time can ripple across billions of light years, and yet the universe holds. The orbits of planets remain stable for eons. The Milky Way's spiral arms trace perfect logarithmic curves. From the fall of rain to the spin of clusters, the weak force of gravity orchestrates everything with improbable harmony. Its dominion extends even to light, which technically has no mass, but carries energy, and energy curves space too. That is why starlight bends around galaxies, why black holes cast shadows, why we can see the same distant quasar appear in multiple places at once. Gravity does not discriminate. It bends photons as easily as planets. The night sky is quite literally warped by its compassion. And still, the story is not finished. In the last few decades, astronomers discovered that the universe's expansion is speeding up, driven by something they call dark energy, a new mysterious component that acts like repulsive gravity. The balance that once favored attraction now leans toward acceleration. Yet even in this shift, gravity remains the counterpoint, the anchor preventing everything from racing apart into a cold, uniform eternity. Galaxies still cohere, stars still form, and planets still circle their suns because gravity, weak as it is, refuses to let go. Perhaps this is the most profound truth of all, that endurance often outlasts power. Gravity never tires, never switches off, never loses its reach. It doesn't burn or decay. It doesn't depend on circumstance or polarity. It simply exists universal and permanent. Its weakness is its strength, the guarantee that it will not overwhelm the cosmos it shapes. The sun's warmth, the orbit of the moon, the tides of the sea, the structure of the Milky Way, all are consequences of a force so modest, it can only be noticed when multiplied by everything. If the strong force binds the small and electromagnetism colours, the world, gravity, binds the infinite sculpting time itself into arcs and spirals. You owe your weight, your seasons, and your place in the universe to its quiet persistence. It is the softest whisper, and yet the loudest law. The universe could have been a storm of forces, each shouting its dominance. Instead, it chose to listen to gravity's hush, a weakness that somehow rules the strong. Einstein's general theory of relativity is not just a law of physics, it is geometry of existence. Where Newton saw invisible threads of attraction, Einstein saw curves, ripples, and deformations in the very stage on which all motion occurs. In his hands, the universe stopped being a machine of forces and became a landscape, a living geometry molded by matter and energy. At its heart lies an equation that is almost poetic in its symmetry. On the left side, geometry describing how space and time curve. On the right, energy and momentum describing how matter moves and radiates. Each side speaks to the other like partners in a cosmic dialogue. Matter tells space how to bend, and space tells matter how to move. It is one of the simplest and most profound relationships ever written, the balance sheet of the universe itself. From this single equation, all of relativity unfolds. Stars orbit because they follow the curves that the sun's mass sculpts in space-time. Light bends because its straightest possible path, its geodesic, is no longer straight in this curved geometry. Time slows in valleys of gravity and runs faster in high planes of space. The closer you stand to a massive object, the more space-time stretches beneath your feet, pulling time itself into the well. To test this vision, scientists have spent a century throwing everything they could at Einstein's geometry, and it has never once cracked. In 1919, starlight bent exactly as predicted. In 1976, NASA's Gravity probe confirmed time dilation by comparing clocks on rockets and Earth. In 2011, Gravity Probe B detected the subtle twisting of space-time around Earth's rotation, a phenomenon called frame dragging, where a spinning mass drags the fabric of space around with it like honey swirling around a spoon. Even the minute precession of Mercury's orbit, off by 43 arc seconds per century, fits perfectly into Einstein's curvature. The more we looked, the more the evidence deepened. Pulsars spinning neutron stars the size of cities, but heavier than the sun, have become nature's laboratories for relativity. When two of them orbit each other, their pulses act like clocks accurate to a billionth of a second. Over decades, astronomers have seen their orbits shrink as the pair loses energy through gravitational waves ripples in space-time predicted by Einstein himself. The rate of that loss matches the equations exactly. Then, a century after his prediction, came the sound of confirmation. In September 2015, the LIGO detectors in the United States caught the faintest tremor in spacetime's fabric, two black holes colliding 1 billion light-years away. The vibrations stretched and squeezed the Earth by less than 1,000th the width of a proton, yet the signal matched Einstein's formula to the last decimal. Since then, dozens more have been heard, colliding stars, collapsing giants, each confirming that spacetime behaves like a cosmic ocean, carrying waves of geometry through its depths. Relativity does not stop at grand scales. It reaches into our daily lives. Every time your GPS calculates your position, it accounts for both special relativity satellite clocks moving fast through orbit and general relativity, their altitude in weaker gravity. If these corrections were ignored, your location would drift by kilometers every day. Even the synchronization of financial networks and global communications depends on time running at slightly different speeds in different gravitational potentials. The theory that once seemed abstract has become indispensable, but this perfection hides an unease. The equations of relativity are smooth, continuous, and elegant, ideal for the vast curves of galaxies and the stately fall of planets. Quantum mechanics, by contrast, deals in granularity, uncertainty, and abruptness. When we try to apply both to the same place, the heart of a black hole, or the first instant of the Big Bang, the math explodes into infinities. Space and time, so fluid in Einstein's world, seem to shatter into foam. This is the boundary of modern physics, quantum gravity, the search for a theory that unites the seamless fabric of relativity with the discrete energy packets of the quantum world. Some imagine space-time made of tiny loops woven like a network of Planck-scale threads. Others see vibrating strings, each note corresponding to a particle or a curvature. Both hope to reveal how geometry itself emerges from quantum information, how the smooth map of reality arises from the buzzing of the smallest conceivable scales. Until that unification is found, we live with two masterpieces that do not quite meet at the edges. Relativity rules the cosmic and the slow. Quantum mechanics commands the minute and the fast. Yet both describe truth within their realms to breathtaking precision. Every experiment, from planetary orbits to atomic clocks, confirms Einstein's geometry to astonishing accuracy, better than 1 part in a trillion. Perhaps that is why his equations endure. They are not just about physics, they are about order in the midst of vastness. They tell us that the universe is not chaos, but curvature, that time and space are flexible, patient, and perfectly logical. And they whisper something more, that even the grandest geometry may one day be revealed as another pattern, another scale in the same endless tapestry. When that day comes, when quantum gravity finally completes the picture, it will not replace Einstein's insight. It will simply reveal what he himself always suspected, that geometry too is alive, dynamic, and unfinished. The story of the universe is written not in force but in form. Every orbit, every wave, every moment of time is a line drawn on the bending canvas of reality itself. For all its beauty, Einstein's theory has a flaw, not an error in its logic, but a fracture in its reach. General relativity explains how planets move, how stars collapse, how galaxies dance. It has passed every test ever devised. Yet when we try to use it to describe the tiniest scales of existence, it fails spectacularly. The smooth curves of space-time that Einstein imagined become violent and erratic at quantum scales. Space itself trembles, tears, and froths with uncertainty. The continuum dissolves. This is where physics breaks at the border between the infinitely large and the infinitely small. Quantum mechanics tells us that the universe is built from discrete packets, quanta of energy, quanta of light, quanta of charge. It has its own rules: uncertainty, superposition, entanglement. It insists that nothing, not even emptiness, is truly still. The vacuum hums with virtual particles that flicker in and out of being. It is a world of granularity, probability, and constant fluctuation. General relativity, by contrast, demands continuity. Space and time form a single unbroken sheet whose curvature changes smoothly under the influence of matter and energy. There is no room in Einstein's equations for jittering uncertainties or particles appearing from nowhere. His universe is calm, continuous, and exact. Quantum mechanics is restless, probabilistic, and discontinuous. Each theory works flawlessly within its own realm, but where they meet near black holes inside the first instant after the Big Bang, the mathematics explodes into infinity. Physicists call this the problem of quantum gravity. It is the missing piece, the unfinished theory that must bridge the geometry of the cosmos with the quantum rules of its atoms. Imagine trying to describe a black hole in both languages at once. General relativity predicts a singularity, infinite density, and zero volume, a point where curvature becomes unbounded. Quantum mechanics, however, forbids infinities. Energy levels cannot diverge without limit. Somewhere inside that contradiction, reality must choose a side. But it doesn't. It sits in between, leaving our equation suspended in paradox. To solve it, physicists have tried to quantize gravity, to find a quantum particle that carries the gravitational interaction, just as photons carry electromagnetism and gluons carry the strong force. The hypothetical carrier is called the graviton, a massless spin-2 particle that would ripple through space-time as a quantum of curvature. If such particles exist, they would mediate gravitational waves at the smallest scales, turning Einstein's smooth ripples into discrete vibrations, the atoms of gravity itself. But detecting a graviton is nearly impossible. Each one would interact so weakly that even a detector the size of Jupiter could wait longer than the age of the universe for a single measurable event. Instead, physicists hunt for its indirect fingerprints, tiny quantum corrections to the behavior of gravitational waves or deviations in the polarization of the cosmic microwave background. Faint whispers that the continuum may not be continuous after all. If gravity does have quanta, their influence would appear at the Planck scale, where distances are about 10 to 35 meters, and times are about 10 to 44 seconds. Below these limits, the very concept of before and after ceases to make sense. The fabric of space-time becomes Planck foam, a turbulent sea of microscopic distortions, tiny wormholes opening and closing, bubbles of curvature flickering in and out of being. It is not empty. It is alive with quantum motion. Space itself might be woven from something deeper, a network of microscopic links that behave like vibrating information. Several theories have risen to explain this hidden structure. The most famous is string theory, which proposes that all particles are not point-like dots, but minuscule loops or strands of energy vibrating in 11 dimensions. Different vibrational modes give rise to different particles. One vibration produces an electron, another a quark, another a graviton. In this picture, space-time itself emerges from the harmonies of those strings, a cosmic symphony where geometry is just the music of vibration. String theory has an undeniable elegance. It unites gravity with quantum mechanics under one framework, suggesting that every particle and force is a note on the same fundamental instrument. It even predicts phenomena that could explain dark matter and the unification of forces at high energies. But for all its beauty, no experiment has yet confirmed it. The strings, if real, are far too small to be seen, and the energies required to probe them lie trillions of times beyond what any collider can achieve. Another contender is loop quantum gravity, a homegrown approach that keeps space-time itself as the central player. Instead of strings, it imagines the universe as a web of finite loops of quantum area and volume. At the smallest scales, these loops form a kind of spin network, a granular structure that quantizes space, just as energy is quantized in atoms. In this model, space-time is digital, not analog. Smooth curves emerge only when billions of loops weave together at larger scales. The geometry of the universe is not continuous fabric, but a mosaic of Planck-sized tiles. There are others still: causal set theory, which envisions space-time as a network of discrete events; emergent gravity, which treats gravity as a side effect of quantum information, not a fundamental force at all; and the holographic principle, which suggests that the three-dimensional universe we inhabit might be a projection of information stored on a distant two-dimensional surface reality as cosmic hologram. Each of these theories offers something tantalizing, a glimpse of the mechanism behind curvature, a sense that space and time themselves might be built from something smaller, more elemental. Yet none have yet passed the decisive test. At present, gravity stands alone, majestic and unresolved, too classical to fit inside quantum equations, too fundamental to ignore. Einstein once said that quantum mechanics was spooky, yet he knew that his own theory would one day need to meet it. The two pillars of modern physics are like two languages describing the same world. One speaks in waves and curvature, the other in probabilities and quanta. We can translate phrases between them, but the grammar still fails at the edges. Somewhere at the Planck frontier, there must be a deeper tongue, one that speaks geometry and uncertainty in the same breath. Until then, general relativity and quantum mechanics remain the greatest duet science has ever written. Two instruments, playing in perfect tune except at the point where their melodies overlap. There the music distorts, hinting that an even grander composition waits to be heard. There was a time when the universe knew no difference between light and decay, between magnetism and the weak nuclear force. Long before atoms, long before stars, everything burned at such impossible temperatures that distinctions themselves melted. In that early fire, all the forces we now separate, gravity, electromagnetism, the weak and strong nuclear forces may have been one. It's difficult to picture because our entire experience of reality depends on separation. But physicists can rewind the cosmic clock through equations. As they raise the temperature, something remarkable happens. The mathematical descriptions of the forces begin to converge. Differences in strength fade. At around 100 billion electron volts, the kind of energy that filled the universe, when it was less than a trillionth of a second old, electromagnetism and the weak nuclear force merge. They become a single interaction known as the electro-weak force. For decades, this was just theory, a symmetry hidden behind the cool calm of today's universe. The weak force seemed confined to rare processes like radioactive decay, while electromagnetism governed nearly everything else like chemistry life. They appeared utterly unrelated. But beneath that difference, the equations whispered of unity. In the 1960s, three physicists, Sheldon Glashow, Abdus Salam and Steven Weinberg, found the framework that made it real. They showed that at extremely high energies, the two forces are not separate at all. They are facets of the same field. Only as the cosmos cooled did the symmetry break, giving rise to the distinct behaviors we see today. This prediction was so audacious that it took 20 years to test. The proof arrived not in theory but in steel and magnets beneath the Swiss-French border. In 1983, the CERN laboratory announced the discovery of two heavy particles, the W and Z bosons, exactly as the electroweak model had foretold. These were the carriers of the weak force, and their masses, precisely 80 and 91 GeV, were fingerprints of the Higgs field symmetry breaking. The electromagnetic photon, by contrast, remained massless. The discovery earned Glashow, Salam and Weinberg the Nobel Prize and turned a speculative dream into the foundation of modern particle physics. From that moment, unification was no longer a fantasy. It became a roadmap. If the weak and electromagnetic forces could merge, might the strong nuclear force also join them at even higher energies? Could there be a single, elegant equation governing every interaction? We know the blueprint of reality itself. This idea is called grand unification, and it remains one of the deepest ambitions in science. The mathematics hints that it's possible. When physicists plot the coupling constants numbers that describe how strongly each force acts, they notice something extraordinary. As energy increases, the lines representing the strong, weak and electromagnetic forces begin to converge. They don't quite meet, but they almost touch at around 1016 16 to 10^16 GeV, an energy scale far beyond anything achievable by current technology. If they do intersect there, it would mean that the forces we see today are simply fragments of a single, unified interaction that existed when the universe was still a quantum ember. To bridge that tiny gap between almost and exactly, theorists propose new symmetries, new particles, even new dimensions. The most famous of these ideas is supersymmetry, or SUSY, a concept suggesting that every known particle has a heavier partner, electrons paired with selectrons, quarks with squarks, photons with photinos. These shadow particles would smooth the running of the coupling constants, allowing the lines to meet perfectly. They would also offer an elegant candidate for dark matter, the invisible mass that outweighs visible matter, 5-to-1 across the cosmos. The Large Hadron Collider was partly built to search for them. So far none have appeared, yet nature has taught us patience before. The Higgs boson took half a century to find. The proof of gravitational waves a full 100 years. The silence of supersymmetry may not be rejection, but simply delay. Even without direct evidence, unification remains the compass of modern physics. Every major discovery from the Higgs field to neutrino oscillations has strengthened the sense that the forces are connected at a deeper level. The standard model, now stands as a monument to that idea, an interlocking set of equations that describes all known particles and interactions except gravity. It works to a precision that defies imagination, yet still leaves the biggest question unanswered: why these forces and why these strengths? If the electroweak unification was the first chapter, the grand unification is the second still being written. To achieve it, scientists look to the sky as much as to colliders. High-energy cosmic rays, relic neutrinos from the Big Bang, and the patterns of the cosmic microwave background all carry clues about how the early universe behaved when the forces were still intertwined. Some grand unified models even predict rare phenomena like proton decay, the slow disintegration of matter itself over unimaginable timescales. Experiments in underground observatories such as Super Kamiokande in Japan have searched for these events for decades. So far the proton endures, and yet the equations keep converging. They whisper that nature's diversity might be the cooled remnant of an ancient unity. In that sense, unification is not just a physical goal, but a philosophical one, the belief that the universe in all its complexity originates from simplicity. Perhaps in those first blazing instants there truly was only one law, one pulse from which all others descended. As the cosmos expanded and cooled, that primal harmony fractured into the quartet. We know the strong force building nuclei, the weak force driving decay, electromagnetism, weaving chemistry, and gravity curving space-time. What we call forces might simply be the echoes of a single chord struck at creation, now stretched across the long cooling of time. If someday we find that missing equation, the one that lets the strong, weak, and electromagnetic finally merge, it may not feel like discovering something new, but like remembering something ancient. A pattern we've always been part of. The original unity still written between the constants that hold everything together. In the language of modern physics, unity is symmetry. Every known force can be described as a kind of symmetry in the fabric of nature rules that remain unchanged when we transform our perspective. Rotate a system, shift it in time, boost it to near light speed, and if the equations still hold, a symmetry exists. From symmetry comes conservation, from conservation stability. The universe endures because its laws rhyme with themselves. Grand unified theories. Guts push that idea to its limit. They propose that the three quantum forces of the Standard Model, strong, weak, and electromagnetic, are not separate at all, but are shadows of one greater symmetry that existed in the early universe. At extreme energies, that symmetry would have been perfect. Only as the cosmos cooled did it fracture into the trio we see today. The simplest and most famous of these attempts is called SU5, introduced in 1974 by Howard Georgi and Sheldon Glashow. The name sounds abstract, but it describes a mathematical group of transformations, the special unitary group in 5 dimensions, capable of uniting quarks, leptons, and their interactions under a single framework. In SU5, all known matter particles fit neatly into just 2 symmetrical patterns. The strong, weak, and electromagnetic forces are treated as different aspects of one grand interaction. Their coupling strengths unified at about 10^1610, 16 giga electron volts. SU5 was the first model to make an audacious prediction. If the forces were once one, then the boundaries between matter types must blur. Quarks and leptons, the building blocks of nuclei and atoms, could in principle transform into each other via exchange of ultra-heavy particles called X and Y bosons. This process would allow protons to decay extremely slowly into lighter particles such as positrons and neutral pions. According to SU5, a proton's lifetime should be around 10^31 years, a vast stretch of time but not infinite. That prediction electrified the physics community. Suddenly, stability itself seemed negotiable. If matter could decay even over cosmological ages, the universe was not eternal but gently eroding. Experiments worldwide, giant water tanks buried in mountains like the Kamiokande and later Super Kamiokande detectors in Japan were built to watch for the rare flashes of light that a decaying proton would emit. Decade after decade, none appeared. By the late 1990s, SU5 in its simplest form was effectively ruled out. The proton, stubborn as ever, showed a lifetime longer than 34 years. Yet the dream of unification did not die. The next generation of theories expanded the symmetry further to SU10 and beyond. In these models, all known particles of a single generation, up quarks, down quarks, electrons, and even elusive neutrinos fit into one 16-dimensional representation of the group. This structure was elegant in a way that only nature itself could rival one particle, multiple to one symmetry, one family of matter. Even more compelling, SO10 naturally predicted the existence of right-handed neutrinos, whose discovery decades later through neutrino oscillations would vindicate part of the model's intuition. In these expanded frameworks, proton decay remains inevitable, but far slower lifetimes of 10 to 3 5 or 1036 non 36 to 36 years, perhaps beyond any current experiment's reach. The absence of observed decay does not disprove unification, it only shifts the horizon of patience. Deep underground in mines shielded from cosmic noise, enormous detectors still keep vigil waiting for a flash of light that might take 100 trillion years to arrive. But there was another clue, and not from the underground, but from the equations themselves. If we track how the coupling constants, the measures of each force's strength, change with energy, something extraordinary happens. At low energies, they differ widely. The strong force binds nuclei fiercely. The weak force governs slow decay, and electromagnetism glides in between. Yet as we move upward toward higher energies, these constants begin to drift toward one another. Plot them on a logarithmic graph, and the 3 lines red for strong blue, for weak green, for electromagnetic descend and almost intersect. Not perfectly, but tantalizingly close. Without new physics, they miss each other by a small but undeniable gap. Introduce supersymmetry. However, a framework where every known particle has a heavier partner, and the lines cross at a single point around 10^16 by 10^16 GeV. Supersymmetry smooths the mathematical running of the forces, suggesting that the universe's apparent diversity is indeed the cooled remnant of an earlier unity. This near meeting of the coupling constants is one of the most haunting clues in all of science. It doesn't prove grand unification, but it refuses to go away. It implies that the strengths of nature's interactions are not arbitrary. They are echoes of a single value, imprinted at creation, distorted only by the expansion and cooling of time. To many physicists, this convergence feels less like coincidence, and more like a fingerprint of design, a whisper that the cosmos beneath its complexity still remembers being one. Yet the challenge remains to reconcile that vision with observation. Supersymmetry, like the grand unified bosons it helps predict, has so far eluded detection. No accelerator has yet seen a single superpartner. Each silence lengthens the odds, but also deepens the mystery. For some, the convergence of coupling constants is an artifact of clever mathematics. For others, it is a map pointing toward an energy scale we have not yet reached. If the unification point is real, it carries profound implications. It means that in the earliest fraction of a second, when temperatures soared to unimaginable levels, matter and radiation were governed by a single symmetry so perfect that it could only be broken by the universe's expansion. It means that every spark in a star, every chemical bond, every atom's endurance are consequences of that original fracture. And it means that in principle the laws of physics might be reducible to one equation, not an approximation, but an identity. From SU5 to SO10, from symmetry to supersymmetry, from theory to experiment, the threads are converging. Not yet tied, not yet proven, but close enough to feel the pull. Somewhere buried under all the constants and particles there may lie a single number, a single shape, a single idea that births all others. It is the same dream that has guided science since the beginning, that beneath diversity lies unity, beneath change order, beneath all motion one pattern. The grand unification is not merely a theory. It is the search for the universe's original language, the one in which everything was once the same word. At the edge of knowledge, one final bridge remains unfinished. The strong, weak and electromagnetic forces already hum together in the mathematics of unification, their coupling constants nearly touching. But one force still stands apart, gravity ancient and sovereign, bending not just space but the story itself. It has resisted every attempt to merge with the quantum world, and yet without it, the dream of a complete understanding, a theory of everything, remains just out of reach. The problem is not arrogance but scale. Gravity governs the large galaxies, planets, the slow curvature of time, while quantum mechanics rules the small atoms, quarks, and the restless dance of probability. At ordinary energies, the two domains hardly overlap, but at the Planck scale, where distances shrink to 10^35 to 10^35 meters, and energies climb to test 19 giga-electronvolts. They collide. There, the smooth space-time of Einstein's geometry turns grainy, jittering like static. The calm ocean of general relativity becomes a quantum foam, and gravity, the grand sculptor of the cosmos, dissolves into uncertainty. To bridge that gap, theorists have turned to a radical idea that everything from photons to protons to the fabric of space itself might be made of vibrations. In this view, the universe is not built from point-like particles, but from tiny one-dimensional strings of energy oscillating across multiple dimensions. Their vibrations determine identity. One pattern hums as an electron, another as a quark, another perhaps as a graviton, the quantum of gravity itself. This is string theory, and for decades it has stood as the leading candidate for the unification of all forces. It does not just include gravity, it requires it. When physicists quantized the vibrations of these hypothetical strings, they found that a spin-2 massless particle naturally emerged from the equations. It behaved exactly like a graviton. Gravity was not a stubborn outsider after all, it was encoded in the music of the strings. But the melody demanded a larger stage. For the mathematics to remain consistent, strings needed more than the 4 dimensions we experience. Some versions required 10, others 11 in the broader framework known as M-theory. The extra dimensions, unseen because they are curled up on scales smaller than atoms, might determine the fundamental constants of nature, the masses of particles, the strengths of forces, even the existence of life. In this picture, our entire universe could be a single vibrating membrane, a brain floating in a higher dimensional space. Other brains might drift nearby, each with its own physics, its own constants, perhaps even its own notion of time. Some theorists imagine the Big Bang itself as the collision of 2 such brains, a cosmic chord struck between universes. If true, we are not living in a singular cosmos, but in an infinite multiverse, a vast orchestra of realities, each playing a slightly different variation of the same theme. String theory is breathtaking, but it remains unproven. Its scales are far beyond the reach of any particle accelerator, and its predictions are subtle, buried beneath layers of symmetry and compact geometry. Still, it has transformed how physicists think. It suggests that space-time and matter are not separate, but 2 expressions of one underlying vibration geometry turned to sound. It implies that every force, every field, and perhaps even consciousness itself may arise from the same deep harmony. Yet the search for a theory of everything is more than a scientific project. It is a reflection of the human condition. Across cultures and centuries, we have sought unity beneath variety, the philosophers one behind the many, the music that ties the notes of existence. Ancient mystics spoke of cosmic harmony, of the music of the spheres. The Greeks imagined logos, the rational order pervading all things. Eastern traditions envisioned Indra's net, a web of infinite jewels, each reflecting all the others. Today's physicists speak of vibrating strings and hidden dimensions, but the longing is the same: to see the pattern entire, to understand how everything fits. Perhaps that is what the universe has been teaching us all along, that unity and diversity are not opposites but stages in the same unfolding. The forces that now seem separate were once one. The constants that shape atoms were once indistinguishable. Even life scattered across 1 billion stars may yet prove to be one story told in countless forms. Maybe the final theory will not arrive as a single equation on a blackboard, but as a recognition that the universe is both law and poetry, symmetry and imperfection, form and song. That understanding and wonder are not endpoints, but mirrors, each reflecting the other endlessly. And when we finally glimpse that bridge, whether through mathematics or meditation, through collider data or a quiet night sky, we may discover that it was never just about unifying physics. It was about unifying us, our curiosity, our fragility, our desire to belong to something vast yet comprehensible. The theory of everything may not be a single sentence written by nature. It may be the sound of the cosmos vibrating through itself, and through us still resonating from the first note ever played. Before stars could shine, before atoms could coalesce, the universe needed something subtler than fire, a background hum that would give shape to what was otherwise pure light. That quiet hum is the Higgs field, the invisible architect of mass. Without it, every particle would move at the speed of light, unable to form atoms or planets or bodies. Everything would be motion without memory, light without substance. The Higgs field is what allowed the universe to slow down enough to build. imagine the newborn cosmos still blazing with energy. For a brief moment after the Big Bang, all particles raced freely, massless and indistinguishable. The universe was a storm of pure radiation, but as it cooled around a trillionth of a second after creation, a phase transition occurred. The Higgs field condensed filling space with a constant presence, much like a fog settling over a valley. Every particle moving through it felt a resistance, a drag that slowed its flight. That drag became mass. The stronger a particle's interaction with the Higgs field, the heavier it became. Quarks and electrons gained the inertia that let them form atoms. Do and Z bosons became massive, distinguishing the weak force from electromagnetism. Photons, which do not interact with the Higgs, remained massless, free to travel forever as light. From this single transformation, the universe acquired both structure and variety. To physicists, this field is a cosmic dial that determines everything. Turn its value slightly higher, and the W and Z bosons become too heavy, shutting down the weak force and extinguishing stellar fusion. Turn it slightly lower, and atoms would disintegrate before they could form molecules. The universe's chemistry and life itself hangs on the precise value of this invisible constant. For decades, the Higgs was a rumor in the equations, the final piece missing from the standard model. The theory worked with astonishing precision, yet without the Higgs it was incomplete. The equations that described the weak force broke down unless some field endowed particles with mass while preserving symmetry. Physicists knew the Higgs must exist, but no one had ever seen it. The problem was scale. The Higgs particle, the quantum excitation of the field, was expected to be incredibly heavy, perhaps around 100-200 giga-electron volts, far beyond the reach of earlier accelerators. The search became a generation's pursuit. Then in 2012, the world watched as the Large Hadron Collider beneath the Alps, a 27-kilometer ring of magnets and detectors, announced its triumph. In twin experiments named Atlas, and CMS physicists saw the unmistakable signature of a new particle with a mass of about 125 GeV, matching the predicted Higgs boson. It decayed in fleeting instants, leaving trails of photons, leptons, and quarks, the shimmering footprint of the field that fills all space. That single discovery closed a 50-year circle and completed the standard model, the most accurate theory of matter ever constructed. But it also deepened the mystery. The Higgs field's value, roughly 246,246,246 GeV, seems unnaturally balanced. Quantum corrections from all other particles should push it astronomically higher, perhaps to the Planck scale, 19 GeV. Yet somehow these vast contributions nearly cancel, leaving the Higgs at a gentle, life-friendly energy. Physicists call this the hierarchy problem, a puzzle of cosmic fine-tuning so delicate that it seems to demand either hidden symmetries, new physics, or a deeper principle we don't yet see. It's as if the universe is tuned on the edge of a knife. A tiny shift in the Higgs field's vacuum expectation value would rewrite the rules of existence. If it were slightly weaker, protons would decay faster than stars could form. Slightly stronger, and electrons might merge into protons, erasing chemistry altogether. Instead, it sits in the narrow band where complexity can emerge, where stars burn slowly, where carbon can form, where the elements of life have time to appear. In that sense, the Higgs is both the most ordinary and the most miraculous of fields. It pervades everything everywhere, yet we cannot touch it, cannot switch it off. Its presence defines what it means for matter to exist. The chair you sit on, the bones in your hand, the light bouncing from your eyes, all owe their weight and resistance to this universal background. And yet, there's a quiet humility in its role. The Higgs doesn't dominate or radiate, it simply allows. It is the stagehand that makes every act possible, then steps back into the dark. When we detected its quantum vibration, the Higgs boson, we weren't so much discovering a new particle as hearing the hum of the universe's floorboards. What the discovery revealed was not just a mechanism but a philosophy. The cosmos is not built from discrete parts alone, but from relationships, fields. Talking to fields, forces curving around each other, symmetries, breaking at just the right degree. The Higgs field is the soft-spoken mediator between motion and matter, a reminder that creation sometimes begins not with force but with stillness. Today, particle physicists continue to measure it more precisely, searching for clues that might point beyond the standard model to supersymmetry multiverses or hidden dimensions. Each new collision at CERN is a question whispered into that field, asking why it chose this delicate balance and whether it could have chosen otherwise. Perhaps someday we'll find that the Higgs is not alone, that its quiet tune resonates with other unseen harmonies in higher dimensions, or even across parallel universes where its value hums differently and whole alternate chemistries unfold. But in this one, our Higgs sits perfectly between chaos and silence, granting the universe weight, structure, and time to dream. It is in every sense the quiet architect, invisible, yet indispensable patient, yet decisive, setting the scale for everything that could ever be real. The universe lives by balance, an invisible calibration so exact that it defies imagination. Hidden at the heart of this equilibrium is the Higgs field, the quiet architect of mass. Its average strength, called the vacuum expectation value, is about 246 billion electron volts, a number that looks arbitrary, yet defines everything. Every proton, every atom, every star owes its stability to this particular value. Change it even slightly, and reality itself begins to unravel. This precarious sensitivity is known as the hierarchy problem, one of the deepest puzzles in modern physics. The issue is not that we can't calculate the Higgs value, we can, and the numbers fit observation beautifully, but that the value seems almost impossibly fine-tuned. Quantum mechanics insists that every particle in the universe, from electrons to top quarks, contributes to the Higgs field's energy through constant tiny fluctuations. These quantum jitters should drive its value to astronomically high levels, up near the Planck scale of 10^19 10^19 10^19 GeV. Yet when we measure it, the result is gentle, modest, and utterly life-friendly, smaller by a factor of 10 trillion trillion. It's as if nature had to balance an equation out to 30 decimal places just to make atoms possible. Physicists sometimes call this the fine-tuning problem, because the Higgs value must cancel out the quantum corrections from all other particles with near-perfect precision. If that balance were off by even a fraction of a percent, the consequences would be catastrophic. Increase the Higgs field's strength, and the W and Z bosons become so heavy that the weak nuclear force effectively shuts down. Fusion, the process that powers stars, would never ignite. Decrease it, and the bonds that hold atomic nuclei together would weaken or fail entirely. Matter would decay into a thin, featureless soup of radiation. Between those extremes lies an incredibly narrow corridor, the Goldilocks zone of physics. Inside it, protons remain stable, electrons orbit without collapsing, and the chemistry of life unfolds in a predictable rhythm. Outside it, there are no stars to burn hydrogen, no carbon to form complex molecules, no galaxies to cradle time. In the language of the cosmos, the Higgs value is the key that keeps existence from either freezing or exploding. This exquisite tuning has led some physicists to suspect that the Higgs field's mildness is no accident but a sign of hidden symmetry, supersymmetry. Susie, for example, proposes that every known particle has a heavier partner, each partner's quantum fluctuations cancelling those of its counterpart, protecting the Higgs value from runaway corrections. In this picture, the universe's knife-edge balance is not miraculous but structural, enforced by an unseen mirror symmetry. Yet so far, no collider has revealed those superpartners. Other ideas take a broader view. Perhaps our universe is just one of many, each with a different Higgs value, a vast multiverse of possibilities, most barren, a few balanced like ours. In that scenario, we exist not because the Higgs is perfectly tuned, but because only in worlds where it happens to be right can observers like us arise to notice. It's a humbling, even haunting thought that life is not inevitable, but conditional, dependent on a field that's settled into just the right note out of an infinite symphony. Still, physicists search for deeper reasons. Some wonder if quantum gravity will someday explain the hierarchy naturally, the way relativity explained Mercury's orbit. Others suspect that our equations are only fragments of a larger pattern, and that the Higgs value may not be fine-tuned at all, only misunderstood. Yet the fragility remains. If the Higgs field were to drift even slightly, if its energy minimum shifted or the vacuum we occupy were not the true one, the universe could in theory undergo a catastrophic vacuum decay. In a sudden quantum event, a new lower energy state of the Higgs field could form, expanding at near the speed of light, rewriting the laws of physics as it passed. Molecules, atoms, space itself would be redefined in an instant. The possibility is remote beyond comprehension, but mathematically real, a reminder that balance, even cosmic balance, may one day tip. And yet for now the equilibrium holds. The Higgs hums at its delicate value, neither collapsing nor inflating, neither too strong nor too weak. It allows the stars to fuse the Earth to cohere the breath in your lungs to weigh something. It is astonishing to realize that everything, the sweep of galaxies, the chemistry of love, the rise of consciousness, depends on a number we could write on a chalkboard 246G of M, a value that seems almost chosen not by intention but by the logic of survival. The hierarchy problem then is more than a technical question. It is a meditation on fragility. Why does the universe balance on this knife edge? Why do the equations conspire to keep matter just stable enough light, just massless enough time, just steady enough for awareness to bloom? No one yet knows. But perhaps the answer is not hidden in the equations alone. Perhaps it is in the silence between them, the space where gravity, quantum fields, and human wonder all meet in precarious harmony, holding existence steady for one more heartbeat. Mass in the deepest sense is not a thing, it is a relationship. Every particle's weight, from the mighty top quark to the nearly weightless electron, arises from how strongly it couples to the Higgs field, that omnipresent ocean of potential. The Higgs does not hand out mass like coins, it negotiates. Each particle interacts with it according to its own coupling constant, its Yukawa coupling, a number that measures how much resistance the particle feels as it moves through the field. The stronger the coupling, the heavier the particle, the weaker the lighter. The universe's entire hierarchy of masses, spanning more than 12 orders of magnitude, is encoded in those couplings. The top quark, for instance, couples to the Higgs with a strength close to 1, and so it becomes immense, about 173 giga-electron-volts heavier than an entire gold atom. The electron, by contrast, interacts with the Higgs at a coupling of about 1 in 500,000. It glides almost freely, weighing only half a millionth of a GeV. Between these extremes lies the architecture of matter. The Higgs coupling pattern is the cosmic fingerprint that defines what stuff can exist. If the electron were even slightly heavier, its orbit around the proton would shrink. Chemistry would collapse inward, and molecules would disintegrate before life could begin. If it were lighter, atoms would balloon, and the binding energies that make stable molecules possible would vanish. The balance between proton mass, set mostly by the strong force, and electron mass, set by the Higgs coupling, is a harmony as precise as any cosmic resonance. The quarks, too, owe their diversity to this same conversation with the Higgs field. The up and down quarks, light enough to build protons and neutrons, interact only faintly, but heavier cousins like the strange charm bottom and top quarks couple more intensely, flashing briefly into existence in particle collisions or stellar furnaces before decaying away. Their fleeting lives are not wasted. They lend the universe texture pathways for transformation, a laboratory of possibility. Without the top quark's immense coupling, for instance, the Higgs field itself would not remain stable. The heaviest quark anchors the vacuum it gives the Higgs its feedback, preventing the field from drifting into instability. In this way, mass becomes a mirror of order. Each particle's weight is not arbitrary. It encodes the geometry of its interaction with the rest of creation. The Higgs field doesn't sculpt isolated objects, it sculpts relationships. The universe's tapestry of atoms and molecules is simply how those relationships appear when cooled and slowed into form. Consider hydrogen, the simplest atom, a proton built from 2 up quarks and 1 down quark orbited by a single electron. Its stability depends on 3 Higgs couplings, each tuned differently yet all compatible. The electron's small mass allows its orbit to spread wide enough to form chemical bonds, while the proton's greater mass gives it gravitational presence. Scale these relationships up and you get carbon, nitrogen, oxygen, all dependent on the same web of couplings, all tracing back to the Higgs field's quiet negotiation with every particle. From that interplay emerges the periodic table, a grand map of how the Higgs field chooses to express itself. The differences between iron and gold, between oxygen and silicon, are ultimately differences in how their constituent quarks and electrons interact with the Higgs background. Even the color of the world, the photons emitted and absorbed by atoms, depends on those same masses which define how electrons jump between energy levels. If the couplings were altered even slightly, the melody of existence would change. A stronger Higgs interaction across the board would make everything heavier, atoms, smaller nuclear reactions, faster stars, shorter lived. A weaker one would make matter diffuse, unstable, unable to hold together long enough for life. Between those extremes lies a narrow passage where complexity thrives, a corridor where carbon can bond 4 ways, water can dissolve, and DNA can replicate. So when we speak of mass, we're really describing pattern, the invisible rhythm that lets the universe distinguish between heavy and light, between permanence and flux. The Higgs field provides the beat. The particles dance to it in their own tempos. That choreography is why stars burn gently instead of collapsing, why elements assemble in predictable steps, why chemistry itself has room to play. In a sense, the Higgs field does for matter what gravity does for space. It gives shape to potential. And just as curvature tells mass how to move, the Higgs tells mass how to be. It is a mirror that reflects the order hidden beneath apparent chaos, showing that everything, from a mountain to a heartbeat, is the consequence of tiny precise numbers, Yukawa couplings written in the fabric of existence. Physicists still have no explanation for why these couplings take the values they do. There is no obvious pattern, no elegant formula predicting why the muon is 200 times heavier than the electron or why the top quark outweighs all others combined. Some call this the flavor puzzle, as if nature has chosen its ingredients with no recipe we yet understand. But perhaps that too is part of the design. Diversity allows stability. Variation allows beauty. Without that strange hierarchy of masses, the universe would be uniform, featureless, mute. Instead, it sings from the hum of hydrogen fusion to the resonance of molecular bonds to the beating of hearts made possible by carbon chains. Each note is the sound of the Higgs field interacting differently, with each particle composing a spectrum broad enough for life to exist. Mass, then, is not merely weight. It is order made visible, a mirror of the universe's underlying design. Every atom, every orbit, every spark of thought is the reflection of that quiet negotiation between matter and the field that fills all things. And in its reflection we glimpse not just structure, but purpose, the knowledge that even the smallest constants are written in harmony with the possibility of life. In the first instant after the Big Bang, before time had meaning or light could travel, the universe was not made of matter at all. It was pure energy, a smooth, seething field of potential, like a taut string waiting to be plucked. Out of that potential came everything, space particles, structure, and eventually us. But to understand how energy became matter, we must journey back to a moment so brief it can only be measured in imagination. The first test or 3510 sa or 35 test 10 30 of those seconds when the universe itself inflated like a breath held too long. This period, known as cosmic inflation, was not an explosion in space, but an expansion of space. A tiny quantum-sized region suddenly stretched faster than light, not because anything moved through space, but because space itself grew. In less than the blink of a blink, it ballooned from smaller than an atom to perhaps the size of a grapefruit or even larger. What drove that extraordinary event is still one of the greatest mysteries in physics. One idea is that a field perhaps akin to the Higgs field, or a close relative called the inflaton, momentarily dominated the universe. Its energy density acted like a cosmological pressure, repelling rather than attracting, causing space-time to expand exponentially. For a fleeting moment, this field's potential energy was the universe driving everything outward in perfect uniformity. Then, as it decayed, that energy was released, converted into a storm of particles and radiation, in a process called reheating. Energy became matter. Fields became the seeds of galaxies. The universe caught fire. In that transformation, the Higgs may have played a pivotal role. Its field, once dormant, could have shifted from one energy state to another, a kind of cosmic phase transition like water freezing into ice. As it settled into its current lower energy configuration, it may have transferred its potential energy into the newborn cosmos, igniting the first particles. Some cosmologists call this the Higgs inflation hypothesis, that the same field which now gives mass to matter once drove the expansion that made matter possible. To see how profound this is, imagine the Higgs field as a landscape, a rolling valley, with a gentle dip where it prefers to rest. At the beginning, the field sat high on a plateau, unstable but balanced. When it finally slid down into its stable valley, the energy difference released in that descent heated the universe to unimaginable temperatures. Space itself rang with the echo of that fall. The radiation that filled the cosmos was not added from outside, it was the universe converting potential into presence. This process left faint fingerprints still visible today. The uniformity of the cosmic microwave background, the oldest light we can see, reflects the smooth, even expansion caused by inflation. Tiny ripples in that background, variations in density no larger than 1 part in 100,000, are the fossilized tremors of quantum fluctuations in the inflationary field. Those minute irregularities stretch to cosmic scales by expansion, became the seeds of every galaxy, star and planet that would ever form. In a profound sense, the structure of the universe was written in the quantum noise of its own birth. Inflation also solved puzzles that once baffled cosmologists. Why does the universe look the same in all directions? Why is space so flat, so finely balanced between expansion and collapse? The rapid inflationary growth smoothed everything, ironing out wrinkles and curvatures, much like air inflating a balloon until every patch looks uniform. When the field's energy finally decayed, the expansion slowed, leaving behind a cosmos, both even and stable, ready for the long, slow evolution of stars. Reheating the aftermath of that event was the first true dawn. As the inflationary field's energy transformed into particles, the universe filled with radiation and matter in near equal measure. Quarks and gluons emerged, dancing in a hot plasma. Photons scattered endlessly. The Higgs field cooling alongside them began to settle into its present state, the same field that now gives every particle its mass. From the most violent surge imaginable came the calm laws that govern everything we know. The idea that one field, the Higgs or something like it, could both ignite and stabilize the universe is as poetic as it is scientific. It suggests that creation and structure are not separate acts, but two sides of the same event, the universe expanding, because it must, then condensing because it can. Expansion birthed matter. Matter through gravity later birthed stars and galaxies, and within those galaxies life began to wonder how it all happened, and perhaps it's not coincidence that the same Higgs field that defines the scale of mass might also define the scale of cosmic expansion. The smallest and largest processes, particle interactions and cosmic inflation may be linked by a single physical principle, energy transforming into order. In the quiet of that first trillionth of a second, energy did not merely fill the universe, it became the universe. It wove time from vibration mass, from resistance structure, from symmetry breaking. Every atom you touch, every breath you take, is the cooled residue of that original conversion energy learning how to hold itself still long enough to become matter. So when we say the Higgs gives particles mass, we might also be saying something deeper, that the same mechanism which gave weight to the smallest quark also gave the universe its first breath. The moment when energy became matter was not just the birth of things, it was the moment when potential learned to take form and has been doing so ever since. For 13.8 billion years, the universe has balanced on a plateau of calm. Space expands, stars are born and die, galaxies drift apart, and yet beneath it all lies an invisible stillness. The Higgs vacuum, the background energy of existence itself. Everything we see, touch or measure rests upon this unseen foundation, but that foundation may not be permanent. It may be only metastable, a delicate compromise between being and becoming, a cosmic pause between two possible realities. To understand this tension, imagine the Higgs field as a landscape of hills and valleys. The value it holds today, that 246 GeV that gives mass to every particle, corresponds to a valley that appears deep and safe. But according to the equations that describe it, this may not be the lowest valley. Somewhere beyond the reach of present energy scales, there could exist a deeper one, a true vacuum with slightly less energy. Our universe then might not be in its most stable state, but in a long-lived false vacuum, a fragile equilibrium sustained by the thin crust of cosmic time. If that's true, we are living in a kind of slow miracle. The Higgs vacuum could in principle decay not gradually but instantaneously. A single quantum fluctuation or a collision reaching beyond critical energy could trigger a transition. A bubble of lower energy space would form, expanding at nearly the speed of light, rewriting the laws of physics as it passed. Inside the bubble particle, masses, charge, strengths, even the structure of atoms might differ. Outside, everything would be obliterated before the thought could finish forming. And yet it hasn't happened. For almost 14 billion years, through the formation of galaxies and the flowering of life, the universe has remained serenely intact. The Higgs vacuum, though not perfectly stable on paper, appears practically eternal in practice. Physicists estimate that if decay ever comes, it will happen not in trillions, but in trillions of years. The field is balanced so exquisitely that its metastability feels less like a threat and more like a quiet grace. This long stability is not accidental. The numbers, the Higgs mass of 125 GeV and the top quark mass of 173 GeV, sit near a razor-thin boundary between stability and collapse. A few percent heavier and the Higgs field might have already tunneled into oblivion. A few percent lighter and the vacuum would have been too rigid, freezing the dynamics of the early universe. Somehow nature chose the narrow strip where the universe can both endure and evolve. It's as though the cosmos tuned itself not for permanence but for possibility. And within that possibility lies another mystery: dark energy. The same vacuum that gives mass to particles also carries energy of its own, a faint, pervasive pressure that fills all of space. We feel it as the acceleration of the universe's expansion, a push outward that counteracts gravity on the larger scales. Perhaps this dark energy is related to the Higgs field's latent potential, the leftover tension between what is and what could be. Maybe the universe's expansion is not a separate phenomenon at all, but a symptom of the vacuum's gentle yearning toward equilibrium. If so, our calm night sky is not truly at rest. It is the stillness of something vast and dynamic, balanced between creation and collapse. The galaxies drifting apart are not moving through emptiness. They're carried by the slow swelling of the vacuum itself. The Higgs field that holds atoms together may also be the agent of cosmic acceleration, the same whisper that gives matter its weight, pushing space to grow thinner, colder, and more distant with time. There is a kind of awe in that contradiction, the universe's gentlest field, sustaining both mass and motion, order and expansion. The same invisible presence that keeps your feet pressed to the ground also fuels the dark energy that will one day carry every galaxy beyond view. Stability and impermanence written in the same equation. Perhaps that is the truest nature of the present moment, a metastable now poised between beginnings and endings. The Higgs vacuum may not last forever, but it has lasted long enough for stars to learn fusion, for matter to organize into life, for life to ask where it came from. That span, a few billion years of luminous order in a universe that could have been chaos, is itself a miracle of physics, and so the quiet tension endures. The universe expands into silence, its fate uncertain, but its balance perfect. Beneath every atom, the Higgs field hums, steady, fragile, eternal for now. Perhaps it will hold forever, perhaps it will not. But in this cosmic heartbeat suspended between potential and collapse, the laws of physics have given us the rarest of gifts, a stable place from which to look up to wonder, and to know that even precariousness can be beautiful. In every atom, the universe rehearses the same harmony that ignites the stars. Four invisible forces, electromagnetism, the strong and weak nuclear interactions, and gravity, work together in quiet coordination, from the tiniest nucleus to the grand furnaces of the galaxies. Each plays a part so distinct and so delicately tuned that if any one were altered, the cosmic symphony would dissolve into noise. At the smallest scales, the strong force is the glue. It binds quarks into protons and neutrons, and holds those protons and neutrons together inside the atomic nucleus. Its reach is short, but its grip is absolute. Within a femtometer, it overpowers all others. Without it, the building blocks of matter would drift apart in a cloud of free particles, incapable of forming anything stable. Balancing this ferocity is electromagnetism, the painter of chemistry and light. It keeps the negatively charged electrons tethered to the positively charged nuclei, setting the geometry of atoms and the colours of the world. The same force that shapes the orbitals of oxygen and carbon also sculpts the magnetic fields of stars and the auroras of planets. Its laws are scale invariant, connecting the elegance of quantum mechanics to the radiance of stellar light. Then there is the weak interaction, subtle and essential. Within the atomic nucleus, it enables transmutation, the transformation of one element into another through radioactive decay. In the heart of stars, it mediates the slow conversion of hydrogen into helium, allowing the sun to burn gently for billions of years instead of exploding in an instant. Every photon that warms your skin is born from a reaction that began with the weak force, turning a proton into a neutron, balanced by the whisper of a neutrino, escaping into the dark. And wrapping them all together is gravity, weakest but most far-reaching, sculpting the stage upon which the others perform. It draws the scattered hydrogen of the early universe into clouds, then into stars, compressing matter until the strong and weak forces awaken within. In that compression, gravity provides the conditions for fusion pressure so immense that atomic repulsion yields to nuclear bonding. The first generation of stars the cosmic forges lit the universe because gravity insisted that light must find a way to exist. The four forces are not rivals. They are partners. Gravity gathers the material, the strong force ignites. Its core, electromagnetism, radiates the light, and the weak force regulates the tempo. Together they turn simple hydrogen into the periodic table carbon for life oxygen, for breath iron for planets. The elements in your body were all born of that alliance inside stars that lived burned and died before the sun ever rose. Consider how precisely they cooperate. If the strong force were only a few % weaker, protons and neutrons would not bind. The universe would contain only hydrogen, no carbon, no life. If it were slightly stronger, fusion in stars would run too fast, turning all hydrogen into helium in a cosmic blink. If electromagnetism was stronger, atoms would shrink and chemistry would suffocate. Weaker, and atoms would fall apart, their electrons flying off into infinity. If the weak force was slower, stars would barely shine, leaving the cosmos cold and dark. Faster, and they would burn out before life could form. Even gravity, if adjusted by a hair, would either crush the universe into itself or scatter its matter beyond reunion. And yet here they are, perfectly balanced, not by chance we can measure, but by a coincidence so precise it humbles the mind. From the level of quarks to that of clusters of galaxies, these four forces weave one continuous story, the transformation of simplicity into complexity. The atomic bonds that hold your DNA are the descendants of the same equations that fuse hydrogen in the sun. When you breathe, you are participating in a process begun in the cores of ancient stars, the same collaboration between electromagnetism and the weak force that released the light that nourished the first life on Earth. This harmony has endured for nearly 14 billion years. Every second in every star, gravity keeps the nuclear fire alive, while electromagnetism carries its radiance outward, balancing collapse and explosion in a steady heartbeat of light. Each photon that leaves a stellar surface is a message from that equilibrium, a quantum note in the long song of stability. It is easy to think of the universe as vast and indifferent, but in truth, it is exquisitely relational. Every force that acts upon you is part of the same cooperative fabric that keeps the sun burning, the planets circling, and your atoms bound. The cosmos is not chaos barely restrained, it is order continuously negotiated. And so from the microscopic to the celestial, the same choreography persists: attraction and repulsion, confinement, and release, decay and renewal. The strong force binds, the weak force transforms, electromagnetism illuminates, and gravity conducts. Together they sustain the long stability of now, the serene glowing equilibrium in which stars shine, worlds orbit, and consciousness arises to witness the balance. The fires of the heavens and the chemistry of life are one continuum, separated only by scale. Every atom's stability is a miniature star. Every star's light is the whisper of atoms remembering how to hold together. Across 60 orders of magnitude, from the trembling of electrons in atoms to the spin of galaxies a million light-years wide, the universe obeys the same handful of constants. The same fine structure constant that governs how light binds to matter also dictates how stars shine and how galaxies glow. There is no separate physics for the small and the vast, no private law for the laboratory, and another for the heavens. Everywhere we look, the same equations hold like a single melody carried across octaves that span all of existence. This continuity is one of the quietest, most astonishing facts in all of science. The electromagnetic coupling that defines atomic structure, the gravitational constant that dictates planetary motion, the ratio between the masses of the proton and the electron, each remains unchanged, whether measured in the heart of the sun or in the light of a quasar halfway across the cosmos. It is as though the universe keeps perfect pitch. Our instruments have stretched that harmony farther than any ancient thinker could have dreamed. The SOHO spacecraft, watching the sun for decades, measures oscillations in the solar plasma that depend precisely on how gravity and electromagnetism balance. From those ripples, physicists confirm that the gravitational constant GGG is the same in the heart of a star as it is on Earth's surface to within parts per million. Meanwhile, the Gaia Observatory has mapped over 1 billion stars, charting their motions through the Milky Way with exquisite precision. Each orbit, each gravitational tug is a test of the same physics that governs a falling apple. The curvature of space, the constancy of GGG, the unchanging rhythm of time, all are confirmed across a scale so enormous that the human mind can scarcely hold it. And now the James Webb Space Telescope has carried that verification to the edge of the observable universe. Its deep-field images, galaxies whose light has travelled more than 13 billion years, reveal that even in the earliest cosmic dawn, the same constants ruled. The spectra of those ancient galaxies show the same fingerprints of hydrogen and helium, the same spacing of electron transitions that we see in the lab. Across epochs and distances, the fine structure constant AO 137.035999 alpha 137.035999 AR Ben 37 or 9% remains unchanged within 1 part in 100,000. That number so small, so specific, may be the most universal signature we know. It determines the strength of electromagnetism, how tightly electrons bind to nuclei, how photons scatter in plasma, how chemistry and starlight coexist. If it were even slightly larger, atoms would shrink and fusion would race. Smaller and molecules would unravel. Yet from our experiments on Earth to the spectra of galaxies at the edge of time, an alpha is the same. The universe from the quantum to the cosmic is tuned to one song. We have tested these constants across 60 powers of 10 in size and 13.8 billion years in duration, and not one has changed in any measurable way. The fine structure constant, the gravitational constant, Planck's constant, the speed of light all sing the same notes now that they did when the first atoms formed. It is this astonishing uniformity that allows physics to work at all. Because constants remain constant, light from the farthest quasar can tell us how atoms behaved when the universe was young. There is poetry in this precision. It means that the same numbers that describe an electron's orbit also describe the orbit of Jupiter. The same constants that let hydrogen atom form a bond also govern the collapse of interstellar clouds into stars. The equations of Maxwell and Einstein do not fade with distance. They scale upward gracefully, carrying their truth across the full spectrum of reality. And yet this unity is not monotonous. Across those 60 orders of magnitude, complexity blossoms. Atoms, molecules, planets, biospheres, galaxies, all built on identical scaffolding. The constants do not vary. What they produce does. Out of sameness comes infinite variety. Perhaps that is the most beautiful symmetry of all, that the universe can be so consistent yet so creative. The constants are the grammar. The cosmos is the poetry written with it. As Gaia charts the stars, as Soho listens to the sun, as JWST peers through cosmic time, they are all engaged in the same quiet act of confirmation that the universe speaks one language from quark to cluster, from the scale of 10 to 18 to 10 centimeters, 18 to 10 to 18 meters, to test 2610 or test 126. The fact that those numbers still match, that no crack has appeared in the cosmic scale ladder, is both a triumph of measurement and a mystery of meaning. Somewhere in that seamless continuity lies a hint of wholeness and unbroken logic that has endured since the first second of creation. The constants did not drift, the laws did not fray. The same physics that shaped the first stars now shapes the neurons pondering them. Across all distances, all ages, all magnitudes, the universe keeps faith with itself. When you listen closely to the universe, it doesn't speak in words, it sings. Not metaphorically, but literally every atom, every star, every decaying nucleus hums a note in a vast mathematical harmony. Across the abyss of space, that harmony remains the same because the constants that define it never change. The cosmos is not chaos held in check, it is music held in law. The instruments are everywhere. The spectral lines of atoms are the universe's purest tones, fingerprints of the fine structure constant Asia 1137 alpha. 1137 delum 1137. That number dictates how strongly electrons bind to nuclei, and therefore how light interacts with matter. When electrons jump between energy levels, they emit photons at exact frequencies: hydrogen at 656 nanometers for red sodium, at 589 for gold oxygen in the cool green of nebulae. Multiply those transitions across the periodic table, and you have the spectrum of starlight itself, a cosmic symphony written in wavelength. These are not arbitrary colors. They are mathematics made visible, ratios between energy levels defined by quantum mechanics and electromagnetism. The spectral lines that we observe from the most distant galaxies match those we produce in laboratories on Earth, shifted only by the universe's expansion. Even over 13 billion years, the song has not changed key. At a deeper register, nuclear decay provides another rhythm, a pulse measured in half-lives. The weak force sets the tempo, how fast a neutron turns into a proton, how long carbon-14 lingers before it transforms, how uranium's heart beats over billions of years. The same constants that fix atomic stability also tune radioactive decay to timescales that span from microseconds to the age of planets. Without that spread of tempos fast enough to power stars, slow enough to warm Earth's interior, the universe would be a static chord, not a melody. and above all of it, burns stellar light, the grand orchestra. In a star's core, gravity compresses matter until the strong and weak forces begin their duet, protons fusing into helium through chains of reactions so delicate that the balance between explosion and endurance hangs on a decimal. If the strong force was slightly stronger, stars would exhaust their fuel in a flash. Slightly weaker, and fusion would never ignite. The fine-tuning is extraordinary, a handful of constants aligning so precisely that the sun can burn steadily for 10 billion years, its radiance feeding the chemistry of life on one small world. This harmony of forces, strong, weak, electromagnetic, gravitational, is not random. It is the consistent rhythm of creation, a cosmic score written in constants. The ratio of the proton to electron mass, about 1836, sets the structure of atoms and molecules. The balance between gravitational and electromagnetic strength determines whether a star becomes a red dwarf or a supernova. Planck's constant defines the beat of quantum transitions. Together they compose the universe's time signature, in which every process from the flicker of a photon to the orbit of a planet plays in sync. Even the light that fills the night sky is a kind of music, its frequencies a record of cosmic composition. Astronomers once likened stellar spectra to chords, hydrogen playing its fundamental note helium, the overtones metals adding harmonics. Each galaxy's glow is a measure of how matter learned to sing through the constants of physics. When the James Webb Space Telescope captures the faint infrared whisper of a primordial galaxy, it is hearing a note struck billions of years ago still ringing true. If we could translate all these frequencies, the hum of molecules, the flicker of pulsars, the oscillation of gravitational waves into sound, we would hear a single evolving harmony, the universe's grand fugue of consistency. From the low tremor of black holes merging to the high trill of subatomic transitions, the spectrum would be continuous, each tone following the same physical rules. The philosopher Pythagoras once imagined the music of the spheres, a harmony created by the motions of celestial bodies. He was wrong about the mechanism, but right about the intuition. The universe is musical not in sound, but in symmetry. The constants of nature act as tuning forks, ensuring that every scale, every octave, every star and atom resonate with the same ratios. Fine-tuning is not merely precision, it is rhythm. The ratio of forces, the spacing of energy levels, the timing of decays, all cohere into a structure where existence can persist and evolve. If any note were out of tune, the universe would lose coherence, atoms would fall apart, light would not form, time would lose its tempo. Instead, everything aligns within impossibly narrow limits. It is this steadiness, the way the constants hold their values across time and space, that makes beauty possible. The spectrum of a nebula, the glow of the Milky Way, even the warmth of your body's chemical reactions are all expressions of the same universal score. The laws of physics do not merely allow harmony, they are harmony. And so when you look up and see starlight stretched thin by distance, you're witnessing the most ancient music still playing the vibration of the same constants that shaped the first atoms. It is the melody of being itself, a song without beginning or end, composed in mathematics and performed in matter. Across all of time, the universe has never missed a beat. From the first second after the Big Bang to the glow of galaxies now, the constants that define reality have held steady, never wandering, never weakening, never breaking faith with themselves. If the universe were a clock, it has been ticking for 13.8 billion years without losing even a second of rhythm. The evidence is written in light older than life itself. Every photon that reaches us from the deep past carries a record of the physical laws that shaped it. When we split that light with a spectrograph, whether it comes from a nearby star or a quasar halfway across the cosmos, we see the same signature lines: hydrogen's red, helium's pale gold, oxygen's green. The spacing between those lines is dictated by the fine structure constant of the same number we measure on Earth today. Astronomers have tested this with relentless precision. By examining the light of distant quasars whose photons began travelling toward us, when the universe was young, they searched for any shift in those spectral lines that would betray a change in A, or the proton-to-electron mass ratio. None appeared. Across billions of light years and billions of years of cosmic history, the laws of electromagnetism have not wavered. The same patterns that govern atoms in laboratories also govern the atoms that glowed before our planet existed. Then there is the oldest light of all, the cosmic microwave background CMB, the afterglow of the Big Bang itself. Detected as a faint uniform whisper of microwaves, It is the fossilized radiation from when the universe was only 380,000 years old. Instruments like COBE-W map and ESA's Planck satellite have mapped it in exquisite detail, measuring variations in temperature smaller than 1 part in 100,000. From those fluctuations, scientists can reconstruct the physical constants that shaped the early plasma, the ratio of baryons to photons, the strength of gravity, the density of matter. Every parameter matches what we measure in the modern universe. That harmony across epochs is not inevitable, it is astonishing. The expansion of space has stretched wavelengths by a factor of 1,000, yet the relationships between them remain exact. The physics that froze into place in the first heartbeat after creation still guides the fusion inside stars, the chemistry in oceans, the thoughts inside minds. Even nuclear decay rates set by the weak interaction appear unchanged since the dawn of time. When scientists study meteorites that solidified before Earth formed, the isotopic ratios reveal the same half-lives we observe today. The universe's metronome never skipped, and yet the permanence of these constants is not sterile or mechanical. It carries an almost spiritual resonance, a sense that the cosmos is reliable in a way no human structure ever could be. Civilizations rise and vanish, stars are born and die, galaxies collide and disperse, but the equations stay true. Somewhere in that steadfastness lies comfort, the assurance that while everything living changes, the foundation beneath does not. You can trace that stability in the faint microwave haze that still fills the sky. Every direction you look, every wavelength you tune to whispers the same message the laws have endured. The universe has aged, but it has not drifted. Gravity bends light the same way it did when the first stars burned. Electromagnetism paints colour the same way it did when atoms first cooled. The strong and weak forces hold nuclei together as faithfully as ever. That constancy is what allows memory itself to exist. If the laws of nature shifted even slightly from day to day, no atom would hold shape long enough for life to remember. The permanence of the constants is the permanence of structure, of time, of consciousness. So when you look at the night sky, what you're really seeing is endurance. The light that touches your eyes tonight began its journey billions of years ago under the same physical laws that cradle you now. The cosmos has evolved in form but not in rule. It has expanded, cooled and darkened, yet the blueprint has not changed. In that silent mathematical permanence there is something tender. The universe, vast and ancient, has kept its promises. Its laws have never lied, never faltered, never abandoned the fragile equilibrium that allows stars to shine and minds to wander. It is this constancy, this loyalty of the cosmos to itself that gives meaning to everything else. The constants have held, and because they held, so did we. For more than a century, humanity has been testing the 4 invisible pillars that hold the universe together: gravity, electromagnetism, the strong and weak nuclear forces. Each has been measured, challenged and verified with a precision that borders on reverence. What began as imagination has become experiment. What began as speculation has become symmetry written in data. Start with electromagnetism, the most precisely tested theory in history. Quantum electrodynamics, or QED, predicts how electrons and photons interact, and the results are astonishingly exact. When physicists measure the magnetic moment of the electron, how it spins and reacts to a magnetic field, they find it agrees with QED's prediction to within 1 part in a trillion. That's like calculating the distance from Earth to the Moon, and missing by less than the width of a human hair. In laboratories around the world, every experiment from atomic clocks to laser spectroscopy confirms the same truth. Light and matter behave according to the same laws everywhere, with no measurable deviation. Next comes the strong nuclear force described by quantum chromodynamics, QCD. It governs how quarks bind together through gluons, creating the protons and neutrons that make up all matter. Unlike QED, QCD is too complex to solve exactly, so scientists turn to supercomputers. Using lattice simulations, they map the behavior of quarks in a digital grid of space-time. The results: the predicted masses of protons and neutrons match observations to within a fraction of a percent. The theory even explains confinement, the reason no free quark has ever been seen, and asymptotic freedom, the revelation that quarks act almost independently at extreme energies. In 2004, David Gross, Frank Wilczek and David Politzer received the Nobel Prize for proving that paradox, confirming that the universe's strongest force is also the one that holds itself in balance. Then there is the weak nuclear force whose reach is tiny, but whose consequences fill the stars. The unification of electromagnetism and the weak interaction into the electroweak theory in the 1970s marked a turning point in physics. 3 men, Sheldon Glashow, Abdus Salam and Steven Weinberg, showed mathematically that at high energies the two forces merge into one. That theory predicted the existence of massive carrier particles, the W and Z bosons, which were discovered at CERN in 1983, exactly where the equation said they would be. Decades later, the discovery of the Higgs boson in 2012 completed the picture, confirming that particles gain mass through interaction with an omnipresent field. Each detection was a note in the same symphony of verification. From electrons to neutrinos, from photons to Higgs, nature kept its word. And then gravity, the oldest and most mysterious of all. Einstein's general relativity transformed our understanding of it from an invisible pull into the curvature of space-time itself. For more than a century, every test has affirmed its accuracy. The bending of starlight during the 1919 solar eclipse matched Einstein's prediction to within 10%. GPS satellites orbiting high above Earth must account for time dilation predicted by relativity. If they didn't, their errors would grow by 10 kilometers a day. Even the orbits of Mercury and pulsars align with Einstein's equations down to minute corrections invisible to Newton's simpler theory. But the ultimate proof came a century later, when relativity's quietest prediction finally roared into evidence: gravitational waves. In 2015, the LIGO observatories detected faint ripples in space-time created by the collision of 2 black holes 1.3 billion light-years away. The signal lasted just a fraction of a second, but its shape and decay matched Einstein's equations with uncanny precision. Space itself had vibrated and the instruments had listened. Since then, over 90 such events have been recorded: black holes merging, neutron stars colliding, the universe ringing like a cosmic bell. Each wave carries the same confirmation: gravity behaves exactly as relativity foretold, even under conditions no human can imagine. Together, these achievements form the most extraordinary body of evidence in scientific history. 4 forces, 4 pillars, 1 coherent universe, electromagnetism tested to 12 decimal places, the strong force simulated and verified in the heart of atoms and stars, the weak force unified and observed through neutrinos and particle decays, gravity mapped from planetary motion to the trembling of space itself. Across 60 orders of magnitude in scale, their predictions hold. From subatomic experiments at CERN to gravitational wave observatories spanning continents, the same equations continue to work. And yet each confirmation feels more miraculous than final. Because behind the precision lies a whisper: why does it all fit so perfectly? Every new test strengthens the framework but deepens the mystery. If science is humanity's dialogue with nature, then this is the clearest reply we've ever received. A universe that answers not in words, but in unwavering consistency. The 4 forces may seem abstract, but they are the invisible architecture of our reality. Every sunrise, every heartbeat, every orbit, every breath is a measurement still matching its prediction. A century of testing has not shaken the pillars, it has only revealed how strong they are. There is a point where precision becomes poetry, where the act of measuring the universe becomes an art form of devotion. Humanity has reached that point. We can now test the laws of nature to 1 part in a trillion way, invisible particles born for less than a billionth of a second, and time the flicker of a pulsar to a fraction of a microsecond across the span of galaxies. We have learned to listen to the heartbeat of the cosmos with instruments so sensitive that they can feel the tremor of space itself. But even in this near perfection, the universe refuses to be fully solved. For every decimal place we conquer, a new question opens proof that precision has limits and curiosity does not. Start with the extraordinary reach of our measurements. Quantum electrodynamics QED predicts how an electron's spin responds to a magnetic field, its so-called anomalous magnetic moment. When physicists measured that value, the agreement with theory came within 1 part in 1012. It is the most precise match between mathematics and reality ever achieved. If the Earth to Moon distance were defined by that ratio, we could land within the width of a virus. At the Large Hadron Collider, the world's most powerful scientific instrument, protons collide at energies of 13 tera electron volts, conditions similar to those just after the Big Bang. The resulting showers of particles are mapped to microscopic detail. The Higgs boson's mass has been pinned down to within a few tenths of a gigaelectron volt. The W and Z bosons to even greater accuracy. Detectors track particles whose lifetimes are shorter than a trillionth of a second, reconstructing invisible decays through trails of data. Each run of the collider is a conversation with nature at its most fundamental, and so far the conversation has been calm, no contradiction loud enough to rewrite the laws, yet subtle whispers persist. In 2021, the Muon G2 experiment at Fermilab revealed a tiny anomaly. The muon's magnetic moment deviated from the prediction by parts per billion. That difference, if confirmed, could hint at new particles or forces beyond the standard model shadows, at the edge of physics' most perfect theory. Scientists tread carefully, verifying, refining, waiting for clarity. Meanwhile, in the cosmos, another disagreement has begun to haunt cosmology: the Hubble tension. When we measure the universe's expansion rate using the cosmic microwave background, the fossil light of the Big Bang, we find a value around 67 kilometers per second per megaparsec. But when we measure it by observing supernovae and galaxies in the modern universe, the number rises to about 73. Two methods, both exquisitely precise, disagree by more than their margins of error. Something doesn't fit. Perhaps an unseen interaction in the early universe, or a subtle variation in dark energy, or a small crack in our understanding of how light travels through space-time. Whatever the cause, it reminds us that precision does not guarantee completeness. The numbers can be flawless and still be incomplete sentences. Then there is the quiet enigma of neutrinos. These ghost-like particles stream through you by the trillions every second, barely interacting at all. For decades we thought they were massless. The standard model demanded it. But experiments like Super Kamiokande in Japan and SNO in Canada proved otherwise. Neutrinos oscillate between flavors of quantum metamorphosis that can only occur if they possess mass. Yet their exact masses remain unknown, lighter than any other known particle but not zero. This single fact that neutrinos weigh something forces us to admit our model of physics, brilliant as it is not the full story. Everywhere we look, the pattern repeats. Our measurements have become exquisite, our instruments godlike in sensitivity, and still the cosmos holds a few decimal places back. The magnetic moment of the muon, the missing symmetry of matter and antimatter, the energy of cosmic rays that defy explanation. Even the quantum foam at the Planck scale where space-time itself trembles remains invisible to us. This is what makes science both humbling and hopeful. The tighter we measure, the clearer the edges of our ignorance become. Precision doesn't end the mystery, it refines it. It tells us exactly where to look next. We live in a time when physics straddles perfection and paradox. The LHC confirms the standard model with surgical precision, yet cosmology demands something beyond it. Our constants stay unchanging across billions of years, yet the expansion of the universe accelerates in ways we cannot explain. Perhaps that tension is not a flaw, but a feature, a cosmic invitation. The universe gives us just enough certainty to build, and just enough uncertainty to keep building. The dream of perfect knowledge may never be fulfilled, but in the attempt lies something deeply human, the desire to match our understanding to the precision of the stars themselves. Every time a new experiment tightens the margin, every time a detector hears a fainter whisper, we come a fraction closer to truth, and yet remain far enough away to keep wondering. In the end, the universe may not need to be solved to be miraculous. It only needs to remain consistent enough to let us measure, think, and question in its light. The limits of precision are not the end of discovery, they are where discovery begins. 95% of the universe is invisible, not hidden behind dust or distance, but fundamentally unseen, made of something that does not shine, does not absorb, does not touch light at all. And yet, this unseen substance and pressure shape everything we know. The stars, the galaxies, even the rhythm of cosmic expansion are guided by forces beyond the four we've come to understand. We call them dark matter and dark energy, the twin mysteries at the frontier of modern physics, the shadow half of creation's architecture. You can picture dark matter as an invisible scaffolding stretched across the cosmos. Though it neither emits nor reflects light, its gravity sculpts the galaxies. When we map the sky, we see not a random spray of stars, but vast filaments and voids the cosmic web. Ordinary matter made of atoms clings to that web like morning dew to a spider's thread. Without dark matter, the universe would not have gathered itself. Galaxies would have flown apart before they ever formed. Its evidence appears in every direction. Galaxies rotate too fast at their edges. The outer stars should drift away, but something unseen holds them in orbit. Clusters of galaxies bend light more strongly than their visible mass, allows a gravitational lens revealing invisible weight. The cosmic microwave background shows subtle patterns that only dark matter could produce, the fingerprints of an unseen hand shaping the universe's infancy. We don't yet know what it is. Perhaps a new class of particle WIMPs weakly interacting massive particles long sought, but not yet found. Perhaps lighter axions predicted by quantum theory's symmetries. Or maybe dark matter is not a substance at all, but a sign that gravity itself behaves differently on cosmic scales. Whatever the truth it holds, galaxies together as surely as the strong force binds nuclei a quiet cohesion, operating in the darkness between stars. If dark matter is the universe's skeleton, dark energy is its breath. Around 6 billion years ago, astronomers expected cosmic expansion to slow, tugged by gravity's pull. Instead, the opposite occurred. Galaxies began to accelerate away from one another as if space itself had turned repulsive. This discovery, made through distant supernovae and confirmed by cosmic background data, was as shocking as learning that the ground beneath us is expanding. We still don't know the cause. It could be the energy of the vacuum itself, a property of space predicted by quantum fields. It could be a dynamic field that changes with time, something like a cosmic weather system, invisible but powerful. Whatever it is, it now dominates the universe, comprising nearly 70% of all that exists. The result is a cosmos whose expansion grows faster every moment, stars drifting apart into a deepening quiet. Together, dark matter and dark energy rewrite our sense of balance. The four known forces, gravity, electromagnetism, strong and weak, govern the visible 5%. The rest lies in shadow, steering the universe from behind the curtain. We live in a cosmos whose visible form is just the surface of a deeper structure, a luminous frosting over an invisible foundation. The imagery is haunting dark matter as the scaffolding of creation, a network of filaments, stretching hundreds of millions of light years, binding clusters into superclusters. Dark energy as the tide of dissolution, pulling that web ever wider, thinning its threads as eons pass. Between the two, existence unfolds a delicate dance between attraction and release. Astronomers have traced that balance across time. In the early universe, dark matter's gravity dominated, pulling gas into knots that birthed galaxies. Now in the universe's later chapters, dark energy leads, driving everything apart. Someday its acceleration may render the night sky empty, galaxies receding faster than light, the cosmic web dissolving into isolation. And yet for now the equilibrium holds. The invisible and the visible coexist, tensioned like strings on a violin. The harmony of forces we know plays upon an unseen instrument we barely comprehend. Perhaps dark matter and dark energy are not anomalies, but reminders that even after a century of discovery, the cosmos keeps most of its secrets. That the four pillars of physics, perfect as they seem, rest upon a deeper foundation we have only begun to glimpse. We measure the shadows and the shadows answer. They tell us the story isn't finished, that reality extends beyond our equations into a domain where gravity whispers differently and space itself breathes. The dark frontier is not empty. It is filled with the potential for new understanding, the promise that what we cannot see may yet explain why anything endures at all. For all the perfection, physics has achieved its constant, steady, its predictions flawless. There are murmurs at the edges, whispers that something more may be moving beneath the four familiar forces. These hints are faint, scattered across different experiments and cosmic scales, but together they hum with the same unsettling refrain. Perhaps the universe is holding one more secret. A fifth force, hidden, subtle, and yet to reveal its full face. It begins in the world of the smallest things. At Fermilab, physicists spin billions of muons, heavy cousins of the electron, through a magnetic ring, timing their wobble with absurd precision. According to the standard model, the wobble the muon's magnetic moment should have a value known to 12 decimal places, and yet when measured, it doesn't quite agree. The difference is small, mere parts per billion, but persistent. The so-called muon G2 anomaly refuses to fade, as though some unseen influence slightly nudges the muon's spin. Could that nudge come from a force we haven't yet catalogued? One carried by an unknown particle, a light Zia boson, a dark photon, or some messenger linking visible matter to the dark sector. The idea is speculative but not impossible. Nature has surprised us before. Every time we've believed the list of forces complete, another has appeared, from Newton's gravity to Maxwell's unification, from Einstein's curvature to the quantum weave. The whispers grow louder in other experiments. At CERN's LHCb detector, physicists study the decay of B-mesons, fragile particles made of quarks that live for 1,000th of a trillionth of a second. According to the standard model, B-mesons should decay into electrons and muons at the same rate, since those leptons differ only by mass. But they don't. The data suggest a preference, an unexpected asymmetry that violates what's called lepton universality. Something, it seems, distinguishes between different flavors of matter. If these anomalies hold true, and future data will tell, they could be the fingerprints of a new interaction, a fifth force connecting specific families of particles, or even bridging ordinary matter and dark matter. It might act only at short range, or only on certain particles, explaining why it hides so easily. Meanwhile, at the larger scales, astrophysicists hear the same question echoed differently. When they map the rotation curves of galaxies and the clustering of dark matter halos, the motions sometimes resist explanation, even with dark matter's gravity included. In some regions, galaxies seem too cohesive, in others too diffuse. Some propose that gravity itself might change subtly at low accelerations, as if another force, feeble but long-ranged, helps shape the architecture of the cosmos. Modified gravity theories like MOND and scalar tensor models hint that perhaps the fifth isn't a new force, but an unseen correction to the ones we already know. To test this, scientists have turned to experiments of exquisite sensitivity short-range gravity tests, where millimeter-scale torsion balances measure whether Newton's law holds at the smallest distances. So far, it does almost perfectly, but each new decimal place of precision leaves just enough uncertainty for mystery to breathe. Some setups even use quantum sensors or cold atoms to probe for minute deviations, as if trying to hear a whisper in a hurricane. In parallel, cosmologists seek signs in the cosmic background, in galaxy distributions, in the unexplained alignments of dark matter and dark energy. Perhaps the fifth force is not confined to the laboratory at all, but woven into the behavior of the universe's invisible scaffolding, guiding how galaxies cluster, how cosmic filaments stretch, how matter and vacuum negotiate their silent truce. Each anomaly on its own might be noise, a fluctuation destined to vanish with better data. Yet together they form a pattern of unease, a sense that something lies just beyond our mathematical reach. Physics, for all its beauty, may be incomplete by a single note, one interaction shy of full harmony. If a fifth force exists, it could be the missing bridge between the luminous and the dark, between the physics of the small and the structure of the large. It might connect the muon's trembling spin to the drift of galaxies' different expressions of the same unseen influence, threading the universe from quantum to cosmic. For now, the whispers remain whispers. But the pattern is familiar. Anomalies precede revolutions. The orbit of Mercury once hinted at relativity. The spectra of hydrogen foretold quantum mechanics. Today's tiny deviations may be tomorrow's new physics, the first tremors of a deeper symmetry waiting to be revealed. In the silence between our measurements, the universe may be whispering a new law. We just haven't yet learned how to listen. At the edge of modern physics, a daring idea is taking shape, one that turns the universe inside out. It suggests that what we call reality is not built from matter or energy, but from information. Every particle, every field, every curve of space-time might be a pattern of data woven into the cosmos. And gravity, the gentlest, most mysterious of forces, may not be fundamental at all, but something that emerges from the collective organization of that information, like warmth emerging from the motion of molecules. It begins with a paradox. According to Einstein, gravity is geometry matter, tells space how to curve, and curved space tells matter how to move. But when quantum mechanics joins the conversation, that picture falters. Near a black hole, information seems to vanish behind the event horizon, defying quantum law. Stephen Hawking showed that black holes emit faint radiation, slowly evaporating over time, but the question remains, where does the information go? The answer may lie not in the hole, but on its surface. In the 1970s, physicists Jacob Bekenstein and Hawking discovered that a black hole's entropy, the measure of its hidden information, is proportional not to its volume, but to the area of its event horizon. A strange clue: the more surface, the more information. It was as if the interior were encoded on the boundary, like a 3D scene projected from a 2D film. From that revelation arose the holographic principle, perhaps the most radical concept in theoretical physics. It proposes that the entire universe may work this way, that everything inside a region of space can be described by data living on its surface. Space itself may be a kind of hologram where depth, distance, and gravity are not fundamental ingredients, but emergent illusions produced by quantum information. In 1997, Juan Maldacena gave this intuition mathematical form in what is known as the ADS-CFT correspondence. It showed that a universe with gravity, an anti-de Sitter space, could be exactly equivalent to a quantum field theory without gravity on its boundary. Two different languages describing the same reality, one geometric, one informational. Inside the hologram, curvature and motion appear. On the surface, only data and interactions exist. Space and gravity arise not from being imposed, but from computation. This is where the frontier of physics becomes philosophy. If space-time can be reinterpreted as information, then perhaps gravity itself is a statistical effect, a result of how information organizes. Erik Verlinde, a Dutch physicist, proposed that gravity could be an entropic force emerging from the tendency of systems to maximize information entropy. According to this view, the attraction between masses is not a fundamental pull but a thermodynamic pressure, a result of information rearranging toward equilibrium. Space curves, not because of mass, but because of the changing density of data. To test such an idea seems impossible, yet whispers of consistency abound. The equations of thermodynamics appear embedded in Einstein's field equations. The laws of black hole mechanics mirror those of heat and entropy. Even the quantum behavior of space itself hinted at by the holographic principle carries signatures of informational geometry bits, arranged in patterns that define distance and time. Imagine zooming out from the Planck scale where the universe flickers with quantum uncertainty. Their space-time might look less like a continuous fabric, and more like a network, a vast web of quantum entanglements linking points of information. The closer two regions are entangled, the closer they appear in space. Geometry in this picture is not a pre-existing stage, it emerges from connectivity. Gravity, the tendency of matter to curve space, could be the manifestation of the network seeking its lowest informational cost. Even the cosmic expansion could have roots in this framework. As the universe grows, new information may enter the holographic ledger, stretching the emergent geometry. Dark energy then might not be an exotic field at all, but the entropy of cosmic information increasing as the universe computes itself into higher states. It's a breathtaking thought that reality might be a self-organizing computation, that matter is data condensed, that gravity is the soft logic of information-seeking balance. In such a universe, the fundamental units of existence are not particles but bits woven together by quantum entanglement into the appearance of space and time. If this vision is true, then physics and meaning converge. Every event, every fluctuation, every thought is a reconfiguration of information within a cosmic memory that never forgets. When we observe, we don't just see, we participate in the updating of the universe's code. From atoms to galaxies, from black holes to human minds, all of it might be a single informational fabric, learning how to describe itself. Gravity then is not the first force, but the last illusion, the curvature of knowledge rather than of space. The holographic principle does not diminish the universe's wonder, it deepens it. It suggests that the cosmos is not merely vast, it is coherent, a conversation of data sustained across time. The stars are not only matter burning in the dark, they are messages written in the same informational language that builds your atoms and your thoughts. And perhaps that is the most elegant possibility of all, that everything, the weight of planets, the stretch of time, the shimmer of consciousness emerges from the same hidden grammar of information, whispered through the equations that keep the universe remembering itself. Across every scale, the universe repeats itself variations on a single elegant theme. From quarks locked inside protons to galaxies bound in dark filaments, nature writes in patterns using the same grammar again and again. The constants we've spent centuries measuring the speed of light, the strength of forces, the ratios of masses are not random numbers but motifs in a cosmic composition. Each appears and reappears, echoed in the architecture of atoms, in the orbits of worlds, in the slow unfolding of galaxies. At the smallest scales, quantum fields weave probability into structure. Electrons dance around nuclei in discrete steps, their motion governed by Planck's constant, a rhythm so exact that it defines time itself. At the largest scales, galaxies trace invisible spirals through the curvature of space. their motion shaped by the same gravity that once guided an apple to the ground. The difference is only in tempo. Physics hums the same melody at every octave. The strong and weak nuclear forces build matter. Electromagnetism shapes light and life. Gravity sculpts the heavens. 4 notes in one universal chord replayed across magnitudes of energy and distance. Together they generate the spectrum of existence, from the fusion in stellar cores to the electrochemical sparks of thought. We live inside this harmony, and every atom in us carries the same ratios that govern the stars. Look closer, and the symmetries recur like reflections in a fractal. The spiral of a galaxy mirrors the twist of a seashell, which mirrors the spin of a hurricane. The branching of lightning echoes the branching of trees, and the diffusion of neurons mirrors the web of cosmic filaments. Patterns emerge not by design, but because the same physical laws apply everywhere, shaping chaos into coherence. Even the constants themselves, a GCH, seem to speak to one another. They appear in equations that describe realms far apart yet somehow connected, as if the universe keeps reminding us that its parts are not separate. The fine structure constant determines how atoms radiate light. That same light obeys relativity's limit c. Its curvature through space traces Einstein's equations, which in turn depend on Planck's scale, where quantum and gravity may finally meet. Every path of discovery loops back to every other, converging into a seamless whole. Perhaps this unity is not an accident, but a clue. Complexity might simply be repetition at higher resolution, a self-similar code iterating from the subatomic to the celestial. The universe in this view is not a machine, but a pattern that learns an infinite tapestry where structure arises naturally from symmetry, and symmetry gives birth to meaning. From this perspective, our search for unification, whether through string theory, holography, or quantum gravity, is not merely scientific but almost musical. We are tuning our understanding to the pitch the universe already plays. When we study the constants, we are not just measuring quantities, we are reading the score of existence itself line by line. Consider the vastness of that symmetry. The curvature of space-time echoes the geometry of atomic orbitals. The spin of particles echoes the rotation of planets. The ratio of forces that binds nuclei is mirrored in the delicate equilibrium that binds galaxies. The universe doesn't repeat objects, it repeats relationships. And through those relationships, meaning endures. Across 60 orders of magnitude, the same equations govern the same ratios, endure the same constants sing. From the foam of quantum fields to the foam of galaxy clusters, everything that exists is an iteration of a single logic energy finding balance, information finding form. We often speak of the universe as vast, impersonal, indifferent, but perhaps it is more intimate than we imagine, a grand recursion that includes us as one of its recurring motifs. The hydrogen in our blood once vibrated in the heart of a star. The iron in our veins was forged in a supernova. The neural signals that carry thought are the same electromagnetic waves that shape nebulae and auroras. The pattern has not changed, only its expression. Look long enough, and the distinction between micro and macro fades. What we call laws of nature may be nothing more than the universe remembering how to be itself over and over at every scale. The constants are its memory, and the patterns are its language. In this unity lies a quiet revelation. We are not observers of the cosmos, but continuations of it, structures built from its repeating code. Every heartbeat, every orbit, every photon is an instance of the same law, resonating through different keys. The universe is not many things, it is one thing seen many ways. And that one thing keeps whispering its pattern through all of space and time energy, becoming form, becoming awareness, wondering how it began. Imagine existence as a single piece of music, vast, continuous, and self-composed. At its heart plays a quartet of forces, 4 instruments in perfect counterpoint, strong, weak, electromagnetic, and gravitational. Together they perform the score of reality, a 4-movement symphony that has been playing since the first moment of time. The strong force opens the piece with the deepest note, a pulse so powerful it binds the very core of matter. Within every proton and neutron, quarks are held together by gluon strings of pure tension vibrating with unimaginable strength. Their confinement is absolute, none can ever break free. This first movement is heavy, resonant, the rhythm of permanence. It gives the universe solidity, the beat that turns chaos into substance. Then soft but essential enters the weak force, the quiet woodwind beneath the brass. It changes one particle into another, reshaping the cosmic melody from within. It is the tempo setter of stars, determining how quickly hydrogen fuses to helium, how long light endures. Without it, fusion would stall and the universe would grow cold and dark. With it, the symphony gains duration, grace, and a slow evolving arc. Its whisper carries through radioactive decay, through neutrinos that slip unseen across galaxies, a metronome of transformation. The third voice, electromagnetism, brings color and texture. It is the violin of the cosmos, bright and fluid. It makes light possible, binds atom, drives chemistry, and writes the tones of starlight across the void. Every photon is a note of its melody. Every molecule a chord born of attraction and repulsion. Electromagnetism is what allows complexity, the shimmering motifs of plasma, crystal, and life. It connects matter to radiant, structure to sensation. And finally, the faint but commanding gravity, the cello that anchors all others. Its notes are low, patient, drawn over cosmic time. Though weakest in strength, it gives the music direction, drawing matter together, shaping galaxies, conducting the long crescendo of evolution. Its motif is curvature, the slow bending of space and time, the descent of light around stars, the solemn rise and fall of tides. Without gravity, the rest would drift apart. With it, the harmony holds. Each force alone would produce only monotony. Together, they weave motion into meaning. The strong force builds the instrument's nuclei to resonate. The weak force keeps the rhythm stars to burn. Electromagnetism adds melody, light to illuminate. Gravity conducts the ensemble structure to endure. Their collaboration defines everything. Inside a star, gravity's pressure ignites fusion through the strong and weak interactions, while electromagnetism carries the light outward. In atoms, the strong force binds the nucleus. Electromagnetism holds electrons near, and gravity, though negligible, ties the entire atom to the cosmic stage. Even within us, the same quartet performs nuclear bonds in our blood's iron, electromagnetic currents. In our nerves, weak decays in the carbon that feeds our cells gravity, keeping our feet on the soil of a spinning world. Over cosmic time, this four-part music evolves. The first notes played when the universe was minutes old, as the strong force froze protons together and the weak force set their ratios. The second movement began with the birth of stars, electromagnetism igniting light, while gravity sculpted galaxies. The third, ongoing still, is the long harmony of life, a local improvisation built from the same recurring themes. And the final movement someday may be the quiet diminuendo of expansion, gravity's rhythm fading as dark energy takes the stage, the quartet's sound stretching thin across infinite space. Yet for now, the balance holds. The four forces remain in tune, their interplay constant across 13.8 billion years. Every experiment we make, every observation of a distant quasar confirms that the cosmic instruments are still tuned to the same key. In that steadiness lies beauty. The universe did not choose chaos, it chose coherence. Four forces distinct yet inseparable, each necessary, none sufficient alone. A strong pulse, a weak rhythm, a bright melody, a gravitational baseline, all synchronized into the living continuum of time. When you look at a star, you're hearing that symphony in light. When you lift your hand, the forces move within you, the strong binding your atoms, the electromagnetic guiding your muscles, gravity tugging softly downward. Even your breath carries traces of the weak force's ancient work, the slow fusion that powers suns. The quartet has never ceased playing. Its notes are galaxies, its harmonies are atoms, its silence is space. And we ephemeral listeners made of its music exist because the four voices of the universe never fell out of tune. The universe is fine-tuned but not perfect, and that is why it lives. Its beauty lies not in flawless symmetry, but in the gentle fractures that let time unfold. Perfection in physics would be silence, total symmetry, no change, no history. Every force equal, every particle balanced, every equation resolving into stillness. Such a cosmos would be pure geometry, elegant, eternal, and utterly lifeless. But our universe chose a different song. Somewhere in its opening, instant symmetry broke slightly beautifully. Particles acquired masses, matter outweighed antimatter by a fraction. The Higgs field tilted from uniformity, gravity weakened just enough to let light escape. Out of those infinitesimal imperfections came motion structure and eventually consciousness. The cosmos works not in spite of a symmetry, but because of it. Consider the matter-antimatter imbalance. For every billion particle-antiparticle pairs created in the Big Bang, one extra matter particle remained. That one in a billion excess became everything: the galaxies, the stars, the bodies that now ponder their origin. Had the symmetry been perfect, all would have annihilated into light, leaving only radiation in an empty sea of equilibrium. Instead, the slight misstep in nature's balance became existence itself. Or take the force's 4 distinct strengths, not one. Their unevenness is what drives evolution across scales. The strong force binds nuclei tightly, but electromagnetism's weaker pull lets electrons dance at a distance, enabling chemistry. Gravity's weakness allows vast structures to form, slowly giving life time to evolve. Even the weak interaction's fragility is essential. It paces the sun's fusion gently enough for stars to endure billions of years. Each imperfection in strength is a permission for complexity. Symmetry breaking runs deeper still. At high energies, all forces may once have been united, their differences hidden. As the universe cooled, those symmetries fractured like ice forming patterns on a pond. Each break created new laws, new particles, new possibilities. The very fabric of space carries the memory of those ruptures, domains, fields, constants that remain slightly misaligned but beautifully consistent. This principle of asymmetry giving rise to order threads through everything. Crystals grow because of imperfections that seed them. Galaxies spin because density wasn't uniform. DNA mutates because copying isn't perfect. Stars flare, rivers flow, and thoughts arise because the universe never settles into exact equilibrium. Perfection is sterile. Imbalance is fertile. Even time itself is born of imperfection. In a perfectly balanced universe, every process would be reversible. There would be no before or after. But entropy, the slow drift toward disorder, breaks that symmetry. It gives direction to existence, turning potential into history. Every sunrise is an echo of that first broken symmetry, the universe still relaxing toward balance, never reaching it. And yet the balance is close enough to endure. The constants are stable to 1 part in 10 quadrillion. The laws are consistent across 13.8 billion years. The universe teeters at the edge of perfection, steady enough for order, imperfect enough for change. That narrow in-between is where everything happens. Stars ignite elements, fuse, life awakens. In that sense, the cosmos is not an engineered machine, but a living tension. Its near symmetries hum like strings pulled just out of tune, producing resonance instead of monotony. The fine structure, constant, not quite rational, the cosmological constant, not quite zero each deviation, a note of dynamism in the song of being. Our existence depends on that unevenness. If gravity matched electromagnetism perfectly, atoms would collapse or fly apart. If matter and antimatter had been born equal, the universe would be nothing but light. If the Higgs field were balanced precisely at zero, no mass would exist. Particles would move at light speed, never forming structure. The universe thrives because it missed perfection by just enough. We too are part of that creative imperfection. Our bodies are products of broken symmetries, our minds instruments of imbalance, neural signals always oscillating between opposites, never static. To live is to participate in the universe's slight misalignment, to ride the edge between order and chaos. When we speak of fine-tuning, we usually mean precision, but the deeper truth is grace, a harmony made of near misses. The universe is not perfect, it is possible, and possibility by its nature requires room to move. Perfection would have ended before it began. Imperfection, gentle and measured, is what lets the universe breathe. It is why time flows, why stars burn, why atoms bond, and why minds wander. The cosmos endures because it leans ever so slightly away from symmetry, forever incomplete, forever alive. Science is the art of finding poetry that can be measured. Its verses are not written in words but in numbers, constants, that never change, ratios that repeat across eternity. The deeper we look, the more we realize that the beauty of the universe is not in its mystery alone, but in its precision, in the fact that nature allows itself to be described again and again with the same unwavering exactness. Every constant is a stanza in this mathematical poem. The speed of light, sastumunanen 792-444 wet demisti s2nanen 792-449 me stumaneni 70 450 yams immutable and precise to the last digit, connecting space and time in perfect proportion. Planck's constant H6 times Q y of 1034 just C2 T n 6.62 seconds when our times yam later. 620 also CDO type is the smallest quantum of action, defining how energy comes in discrete steps like the rhythm of a metronome. The gravitational constant G 6.6 motorland 11 in Zidot PM tools KGG 66444 times their space and 11 klaren. The cotton Dursten text Kionterush gas tests 6744 test on tests mal 11 SCs.T M2 2 so faint and yet so universal that it binds galaxies and governs the fall of an apple in the same breath. Then there is the fine structure constant ASM 436 alpha Yaprox. 37 Melor 137 dimensionless mysterious, the signature of electromagnetism's strength. Physicists have called it the handwriting of God, not out of theology, but out of awe, a pure number that dictates the shape of chemistry, the glow of stars, the possibility of life. If it were even slightly different, the universe's melody would play in a different key. What makes these numbers miraculous is not their immensity or smallness, but their consistency. Every lab, every century, every measurement finds them the same. When light bends around a distant galaxy exactly as Einstein's equations predict, or when a clock on a satellite runs slower by precisely the amount, relativity demands we witness the most profound kind of beauty, the kind that repeats. Repetition is not dullness. It is reliability, the heartbeat of truth. A hydrogen line measured in 1950 is identical to one measured today from a quasar 13 billion light-years away. The decay rate of carbon-14 remains constant through millennia, allowing us to read the age of bones and trees. The ratio of the electron's charge to its mass never wavers, binding modern circuits and ancient starlight to the same physics. To some, this precision feels mechanical. To others, it feels sacred. It means the cosmos is readable, its logic shareable across minds and eras. Each decimal place is a promise kept that nature will behave tomorrow as it does today. We build civilizations upon that faith. The bridges that stand the GPS that guides the spacecraft that lands on Mars all rely on constants that do not drift. But precision alone is not what makes science beautiful. It is the interplay between measurement and meaning, between the instrument's tick and the imagination's leap. When a number measured in a cold lab mirrors a process inside a distant star, the two ends of the universe meet. In that instant, mathematics becomes emotion, the recognition that we the measurers are part of the measured. This is why physicists sometimes speak of measurable miracles, not supernatural events, but moments when nature's order reveals itself with almost impossible clarity, the 1 in a trillion agreement between theory and the electron's magnetic moment, the matching spectra of ancient galaxies and laboratory atoms, the identical waveforms of gravitational waves predicted a century before they were heard. These are miracles born not of faith, but of accuracy, beauty that can be verified. Each experiment is an act of listening, each constant a note held across cosmic time. The equations that describe them are verses of a universal poem, E MC2E, MC2E for MC2, a sentence so concise it binds matter to light, FGM 1M 2F, G frac M mem M2, Re 2, GR2 mem 1 M2, a whisper that unites falling apples with orbiting worlds, E Hen Mono, and the promise that every photon carries its song at just the right pitch, and all of them rhyme. Science at its core is not the conquest of mystery, it is the crafting of language precise enough to describe wonder without diminishing it. Each constant is a bridge between the abstract and the real, between thought and cosmos. In the end, the beauty of the universe is not only that it exists, but that it can be measured, predicted, and remembered. Its poetry is written in decimals, its verses in recurring laws, its rhythm in repeating experiments. When the same number appears in every corner of creation, it is as if the cosmos is reciting its favorite line, a proof that even in infinite complexity there is harmony, and that the miracle of existence is measurable after all. Even after centuries of equations, experiments, and revelations, our map of the universe remains unfinished. Its edges blurred, its heart still hidden. We have traced the outlines of reality across 60 orders of magnitude, from the trembling of quarks to the sweep of galaxies, yet vast regions remain unexplored. The further we advance, the more we realize that the frontier of knowledge is not a line we cross, but a horizon that recedes as we approach. At the edge of that horizon waits quantum gravity, the great unifier that refuses to be tamed. General relativity describes the smooth geometry of space-time, while quantum mechanics describes the grainy chaos of particles and fields. Both are true, both complete in their own realms, and both break down when combined. Near black holes or at the Planck scale, the two languages clash, one continuous, the other discrete, one deterministic, the other probabilistic. Between them lies a silence where mathematics has yet to find its voice. Physicists dream of bridging that divide. String theory imagines every particle as a tiny vibrating filament, uniting gravity and quantum mechanics within 10 or 11 dimensions. Loop quantum gravity reimagines space-time itself as a network of quantized loops, a geometry built from discrete bits of area and volume. Others look to emergent gravity, where space-time is not fundamental, but arises from entanglement from information itself. Each approach offers glimpses of coherence, none yet provides the final chord. We are perhaps like musicians who know the melody by heart but have lost the last note. Beyond even that lies the enigma of the dark sectors, the unseen majority of existence. Dark matter, the invisible mass that holds galaxies together, has never been directly detected. Dark energy, the quiet pressure accelerating the universe's expansion, remains unmeasured in origin and nature. Together, they make up 95% of all that is yet we have names not understanding. For all our precision, we are studying the world through a keyhole, watching the faint glow of a much larger reality. And still, we continue guided not by certainty, but by curiosity. The humility of physics is its greatest strength. It accepts what it does not yet know. Each mystery, each unclosed equation, each unconfirmed anomaly is an invitation, not a defeat. Our instruments grow more sensitive, our models more intricate, but what sustains the journey is not the illusion of mastery, it is the wonder of not knowing. We stand now on a precipice of possibility. The detectors at CERN may glimpse new particles that hint at extra dimensions or hidden forces. The next generation of observatories, Euclid, Vera, Rubin, James Webb and beyond, may reveal how dark energy evolves, or whether it even exists as a separate entity. Gravitational wave telescopes may capture the echoes of the Big Bang itself, letting us hear the first vibration of space-time. The unknown is not emptiness, it is potential waiting to take form. The map we have drawn so far is astonishing. It explains the fusion in stars, the chemistry of life, the expansion of galaxies. But when we zoom out, we see the blank regions labeled terra incognita quantum gravity, the origin of time, the nature of dark matter, the fate of consciousness, the ultimate unity of information and energy. Each blank is a promise that the story isn't over, and perhaps it never will be. For every question answered, another arises, the constant recursion that keeps knowledge alive. The universe does not reveal itself all at once. It unfolds in layers, each one demanding deeper humility. The more precisely we understand the laws, the more miraculous it seems that such laws exist at all. In that humility lies our truest kinship with the cosmos. We too are made of unfinished equations, beings of pattern and uncertainty, small enough to question, vast enough to wonder. Our instruments may measure the constants, but our minds measure meaning, and both are incomplete without the other. So we continue to explore the edges, knowing they will move as we do. Perhaps the universe will always keep a portion of itself beyond reach, not to frustrate us, but to ensure that curiosity never ends. The unknown is the universe's way of staying alive within us. We have mapped the visible world, tested its constants, confirmed its harmony. Yet standing before the unfinished horizon, we must whisper what every scientist eventually learns to say, with reverence, not resignation. We do not yet know, and that too is beautiful. After all the equations, the experiments, the questions that still hang in the dark, what remains is balance. A cosmic balance sheet spanning from the smallest quark to the widest supercluster, where every entry matches, every constant reconciles. Across unimaginable scales, four forces and their unbroken order sustain a universe that not only endures but sings in equilibrium. At the smallest scales, the strong force rules the unshakable accountant of matter's integrity. It binds quarks into protons and neutrons, then locks them into atomic nuclei. Its strength is fierce, but confined. It never overreaches. It holds fast at a distance measured in femtometers, keeping the atomic core tight and steadfast. Without it, the ledger of matter would collapse to dust. The electromagnetic force follows, governing everything from atomic bonds to light's passage through glass. It is the universe's communicator, translating the invisible structure of matter into the visible radiance of stars. Between attraction and repulsion, it creates balance at human scale, chemistry, electricity, magnetism, color, and life. Its domain is infinite yet delicate, its constant A is a 1/137, precise enough to make a stable cosmos, and vibrant enough to fill it with variety. The weak force works in the shadows, adjusting the ratios, setting the pace. It changes neutrons to protons, fuels the slow fusion in the sun, and sows the seeds of transmutation. Its touch is faint but essential. Without its soft recalculations, there would be no energy, no evolution, no starlight lingering long enough for life to begin. It is the universe's quiet editor, ensuring that creation remains dynamic, not static. And presiding over all gravity, the final arbiter, the patient reconciler of scales. It is weak, yet it cannot be denied. Its reach is endless, linking every atom's mass to the motion of galaxies. Gravity holds together the stars born of nuclear fire, keeps planets in their orbits, and curates the architecture of the cosmos. It brings the sum of creation into focus, the ledger balanced from the fall of an apple to the bending of light around black holes. Each force governs a distinct domain, but their borders overlap like the instruments of an orchestra sharing resonance. The strong builds the foundation, the electromagnetic adds design, the weak keeps time, gravity provides the theme that unites them all. Together they span the hierarchy of nature, transforming energy into form into motion into meaning. We can now measure their harmony with exquisite fidelity. The strong coupling constant matches experiment to within a fraction of a percent. Electromagnetic predictions hold true to 1 part in a trillion. The weak interactions' fingerprints appear exactly where theory foretold. General relativity's curvature fits the cosmos down to the wobble of pulsars and the faint murmur of gravitational waves. From the smallest quantum fluctuation to the largest cluster of galaxies, the numbers align. Across 60 powers of 10, the same constants repeat their truth, steady, loyal, and endlessly verifiable. And yet it is not precision alone that moves us. It is the awareness that this balance was not guaranteed, that the strengths could have mismatched the constants, drifted the harmony never formed. Instead, the cosmos found a configuration so exact, it permitted chaos to become pattern, simplicity to become story. We stand within that story. Every breath, every heartbeat, every starlit night is proof that the cosmic accounts are still in order. The same forces that govern the spin of galaxies keep our atoms bound. The same constants that shape light also define our vision of it. Between the infinitesimal and the infinite, the equations close. And perhaps that is the universe's quiet gift to consciousness, the knowledge that balance need not mean stillness. The cosmos evolves, expands and transforms, yet its core arithmetic never wavers. The harmony of forces does not freeze creation, it sustains it. It allows for stars to live and die, for matter to cycle through light and dust, for minds to awaken and wonder how it all holds together. If there is a moral to the mathematics, it is this: existence endures, because the universe keeps its books balanced with breathtaking care. The strong binds the weak, transforms, the electromagnetic illuminates, and gravity unites. 4 forces, 4 signatures of order, cooperating across the abyss. And within that measured harmony against the infinite silence of space, something extraordinary happens. Atoms align, galaxies turn, and life begins to understand the music that made it possible. Part 35. Close your eyes and let the universe hum around you. All that you are, every heartbeat, every atom, every quiet thought is held in place by 4 gentle forces that have never once fallen asleep. The strong force keeps your matter whole. Deep within each nucleus, it binds protons and neutrons with patient certainty, a bond so loyal it has endured since the dawn of time. The electromagnetic force hums softly through you, shaping every breath, every flicker of thought, every spark of light that reaches your eyes. The weak force continues its invisible rhythm, transforming particles in the heart of stars, turning fuel into radiance that drifts across space to warm our small world. And gravity, steady and low, like the tone of a cello, holds everything in its arms. Earth beneath you, the moon above, and the galaxies turning slowly beyond your dreams. For billions of years, these 4 companions have watched over creation without pause. They ask for nothing, they rest in nothing yet. Through their harmony, the cosmos remains intact. They are the quiet caretakers of existence, keeping the balance while all else changes. Tonight as you lie, still remember that the same equations that guide planets also guide the particles in your blood. You're not separate from the universe. You're one of its expressions, a brief luminous thought in its long and measured mind. The stars outside your window burn because of gravity's pull and the strong forces embrace. Their light, born from the weak interaction, travels on waves of electromagnetism before touching the fragile surface of your eyelids. Even in the dark, you're woven into that journey. Everything holds, everything continues, the constants remain true, the forces hum in perfect time. So breathe deeply, knowing that the universe is steady beneath your rest. Its great mechanisms do not falter, its ancient balance endures. Sleep while the strong force keeps your atoms close. Sleep while electromagnetism carries the quiet music of your nerves. Sleep while the weak force turns the hearts of stars. Sleep while gravity holds you gently against the turning earth. For as long as you dream, the four forces keep their vigil. They cradle galaxies and candle flames alike. They make stillness possible and motion inevitable. Good night, traveller of stardust. Good night, child of the same physics that spins the heavens. The cosmos is calm tonight and you are safe within its laws. Subscribe if I helped you sleep. Don't forget to comment where you're watching from and what time it is for you.